chaos rather beautifully. So instead of giving you a brief review, let me just show you the simulation. So this is basically a simulation of two balls inside a spherical box. And the spherical box is perfectly reflective. And the two balls, they are actually slightly off the vertical axis, and they are transparent to each other. The difference in the initial position is so small that you cannot even see two's ball now, or even in first few seconds. So let's start the simulation. So this is classical chaos. Nearby trajectories diverge exponentially fast in time. On the other hand, quantum chaos is a lot more subtle, mainly because our classical intuition of chaos does not work anymore. In physics, whenever we want to have a quantitative understanding of any concept, the first thing that we need to figure out is the right observable. Thankfully, we know for a long time that out-of-time order thermal correlators are good measures of quantum chaos. For example, OTOs is like this. So it's a 4-point out-of-time order correlator. We have two different operators, V at t equals to 0 and another operator W at t. And all the operators are simple operators. And rho here is the thermal density matrix, and B is 1/, temperature. So this specific OTOC was first introduced by Maldacena, Shankar, and Stanford in their famous 2015 paper. As you can see, this is a regularized version of the OTOC that was initially introduced by Larkin and Ovchinnikov in 1969. The main advantage of this specific OTOC is that it gives us some amount of mathematical control. It has some very nice mathematical properties. Because of that, we have some amount of control. Because of that, this quantity has been extensively analyzed over the last several years, and generally it is believed to be a very good measure of quantum chaos. So in this talk, I'm going to use this observable to describe quantum chaos. Physically, what this OTOC does, it measures the effect of a small perturbation created by the operator V at t equals to 0 on another operator W at a later time t. So that's physically, roughly speaking, physically what it measures. So this is the outline of the rest of the talk. In the first part of the talk, I'll discuss universal bounds on chaos and how to find them. In the second part of the talk, I'll discuss saturation of these bounds, which will lead to the idea of extremal chaos. And I'll also discuss what can we learn about quantum gravity from this exercise. Okay, so I'll only consider thermal quantum systems with a large number of degrees of freedom and simple Hamiltonians. If we want to talk about quantum chaos in a sensible way, we need a large number of degrees of freedom, because that's when we can talk about small perturbations. In such systems, there are two timescales that are of importance to us. First is the distribution time, t subscript d. It is the time scale above which thermal 2-point functions decay exponentially fast. Also above the distribution time, all time-ordered correlators, they factorize. Roughly speaking, the distribution time is parametrically of the same order of beta, where beta is inverse temperature. For chaos, the relevant time scale is when t is much, much larger than this distribution time. So before that, chaotic dynamics is not important. So chaotic dynamics becomes important only when you wait for a long time. And this star is the scrambling time. It's the time scale when when quantum chaos is the dominant effect. So for our purpose, we will focus on this particular time scale, but t is much, much larger than the dissipation time. A quantum system is said to be chaotic when the OTOC has this particular behavior. Initially, the OTOC is almost constant and it's given by the factorized value. After the onset of chaos, the OTOC starts to decrease. And at the scrambling time, the OTOC deviates significantly from the initial factorized value. And after the scrambling time, OTOC decreases further, and it becomes vanishingly small if you wait for a long time. Another point that I should have mentioned before is basically for the class of system that we are considering, these two time scales, the dissipation time and the scrambling time, they are parametrically separated. Since the scrambling time goes as log of entropy, and dissipation time is of the order of beta, so we can see that there is a large separation between these two time scales. Also, the OTOC exhibits a period of Lyapunov behavior, just like classical chaos. At least it is expected to exhibit this Lyapunov behavior for theories that are chaotic. So that behavior is the following. So obviously we have this factorized value, which is time independent, and then there is this exponential piece, which is the Lyapunov behavior. This lambda L is the Lyapunov exponent of quantum chaos, and this n is an effective measure of number of degrees of freedom. And this is expected to be true for all chaotic systems for t much, much larger than the dissipation time and much, much smaller than the scrambling time. So in some sense, this Lyapunov behavior is a semi-classical effect in quantum chaos. It is well known that the OTOC is notoriously complicated. After all, quantum chaos is very complicated. So it is rather remarkable that there is a universal bound on the rate of growth, rate of change of this OTOC. This is the famous Maldacena-Shanker-Stanford bound on chaos. This is also known as the MSS bound. That bound tells us that the Lyapunov exponent of chaos is bounded from above by 2 pi over beta. Conceptually, this is remarkable because this implies that quantum chaos in any system cannot grow arbitrarily fast. There is one more reason conceptually why this is very important. For a long time, it is believed that quantum gravity is maximally chaotic. So this MSS bound provides a precise definition of the term maximally chaotic. So these are the systems that saturate the MSS bound. However, there are many reasons to believe that our understanding of quantum chaos is incomplete. To see that, let's look at the OTOC again. So obviously, this is the semi-classical piece, and the MSS bound is a statement about this semi-classical piece. But there are these dots. These are the subleading terms in this expression. MSS bound was derived from by using the fact that the OTOC, this OTOC F, is an analytic function which is also bounded in some region in the complex T-plane. However, this semi-classical piece is not bounded. This semi-classical piece by itself is not bounded in that same region. That implies these subleading terms, they are actually very important and they must be there to make the OTOC consistent. And in some sense, these subleading terms, they are completely quantum mechanical effects. So since we are discussing quantum chaos, it will be nice to know something about these subleading terms. And actually, it is very easy to see that these subleading terms must be highly constrained. The reason is it's not that any expansion you write down when you resum will lead to a function which is both analytic and bounded. Analyticity and boundedness condition, they are really strong conditions. So we should expect that these subleading terms should also be highly constrained. This expectation is also supported by some CFT results, indicating that we might be missing infinitely many new constraints. There is a related question which is of interest to all high-energy theorists. So as I mentioned before, maximal chaos provides a bridge between quantum gravity and quantum chaos. However, we practically know nothing about how to analytically continue maximal chaos beyond the scrambling time. Surely this should be of importance in quantum gravity. So the goal would be to gain a better understanding of quantum chaos by addressing some of these questions. So I'll adopt the simplest possible approach that I could think of. It's basically, I'll start with basic properties of the OTOC that are well understood and derive bounds from these properties in a systematic way. In essence, this is very similar to what we do in conformal bootstrap. So again, this is the same OTOC that I showed in the beginning. So V and W, they're simple local Hermitian operators. So just from the definition, one can show that the OTOC must be analytic as a function of complexity in this infinite half strip. So this strip is between imaginary time beta over 4 and minus beta over 4. And it extends for real t to infinity. So that's the first property. The second property is the OTOC satisfies the Schwarz reflection condition, where the bar represents complex conjugation. And the third property is the OTOC is bounded on the boundary of this strip for time larger than the dissipation time. And it is bounded by the factorized value. So this third boundedness condition is related to unitarity, because the way it was derived was basically they started from some positive norm which requires unitarity, and this is basically some kind of Cauchy-Schwarz inequality associated with that positive norm. So then, starting from these three properties, we can derive bounds. And actually, the bounds can be derived and organized in a systematic way by defining these moments of the OTOC, mu. Where this subscript j, you can think of that as spin. So this is basically an integral of the OTOC with some simple kernel along the imaginary direction. And from the three properties that I showed you in the last slide, one can derive some rigorous bound on these moments. When j is 0 or positive integer, all these moments must be positive, bounded, monotonically decreasing as you increase spin, and it's a log convex function of spin. Note that some of these constraints, they are strict inequalities. So these strict inequalities can never be saturated, but some of the constraints can actually be saturated. This will be important later. So, okay, implications. So the MSS bound is actually contained in this infinite set of constraints. To see that, again, we start with this particular specific form of the OTOC. One can easily compute these moments. They are very simple integrals. And if you do that, from the positivity and the monotonicity condition, one can show that the Lyapunov exponent must satisfy the MSS bound. Let's now saturate the MSS bound. Let's see what happens. Then again, you can compute the associated moments. And now the moments, all the moments are zero except the spin zero moment. But as I showed before, the moments must be strictly positive. So this is completely inconsistent with the strict positivity condition. This immediately implies that MSS bound cannot be exactly saturated over any period of time, however short. So the natural thing to do would be to add some subleading terms like this. For C1 and C2, there are some order 1 numbers, and epsilon is some small parameter. It can be some factor of 1/10. It can be some other small parameter. The reason we have this small parameter is to make sure that this second term is basically a subleading term compared to the first term. The first term saturates the MSS bound. Again, we can compute the associated moments. It's an easy computation. And from there, we can actually find another bound on lambda2, where lambda2 is this coefficient here.
Sandipan?
Yes, go ahead.
Question. So you said MSS bound cannot be saturated, and you just said the first term saturates the MSS bound.
Yeah, it cannot be saturated exactly. So saturating it exactly will mean that there will not be any other term like this. It will just have this first term.
Well, I mean, MSS bound is on the first term. So
no, like it depends on how you phrase it. So like there is a way to write it down in terms of derivatives of the OTOC, which should be less than something else. Like you can phrase it without even talking about the Lyapunov exponent. So when I say saturating MSS bound, I mean saturating that the original inequality.
I see. But I thought there is understanding that these subleading terms must be present.
Yeah, whatever I'm saying, it's not really controversial. It's basically like, since we know it's an analytic function and the first term is not analytic in the half strip everywhere. So yeah, it's not something really controversial.
Okay, thank you.
Okay, so the new thing is basically, so there is a bound on this subleading term. So the lambda2 is bounded from above by 6 pi over beta. And there is also a bound on the numerical, there is a sign constraint on the numerical coefficient. And this is also an optimal bound in the sense that there are known systems that saturate this bound. For example, in Arnav's talk, he gave us one such example where this bound was saturated. You can actually derive many such bounds from the bounds on the moments, but because of time, I'm not going to discuss any of them. Instead, let me discuss a more important point. So this infinite set of constraints telling us that we are not using the right language for chaos. So what I mean is the following. So these constraints in terms of the moments, they are completely non-perturbative. However, only way we can implement them or use them is by writing down some functional form of the OTOC or doing some kind of perturbative expansion of the OTOC. So we're still thinking about chaos in a very perturbative way. And because of that, even though we have this infinite set of constraints, we still don't know how to analytically compute maximal chaos. So these are actually very difficult questions, but surprisingly, these two questions are related to a much simpler questions that can be solved exactly. So that's the question about saturations of chaos bounds or these new chaos bounds. So this immediately leads to the idea of extremal chaos, which is a natural extension of the idea maximal chaos. As I said before, maximal chaos is a statement about the leading term of the OTOC. So when the leading term saturates the MSS bound, we have the maximally chaotic OTOC. But as we discussed before, this is only a statement about the leading order approximation, and this OTOC obviously requires analytic completion. So the extremal chaos is a natural extension of this idea. So we have this infinite set of new constraints, and some of these constraints are strict inequalities, which cannot be saturated. But there is an infinite subset of constraints that allow saturation. So the strategy would be to saturate all the constraints that can be saturated without violating any of the strict inequalities. So that's how one can define extremal chaos. To begin with, it is not obvious whether this is even well defined. For example, this problem might not even have a consistent solution. Surprisingly, this problem does have a solution, and that solution is unique. So without going into all the details, let me just show you the final result. If you if you saturate all the bounds that can be saturated without violating any of the other bounds, you end up with this OTOC. So this is completely fixed up to one free parameter T effective, which is a constant time scale. To see what that time scale is, for T much less than T effective, we end up with exactly the maximally chaotic OTOC. But it differs from yes.
So 5 minutes left, yeah.
Okay. But if you for T much larger than T effective, this is completely different from the maximal OTOC. So in fact, this OTOC is well behaved even after the scrambling time. Pictorially, this is how it looks like. So this is the extremal solution. So it becomes minimum at T effective, and it goes up and it goes to FD again. And this dashed red line is the maximally chaotic OTOC, which coincides with the extremely chaotic OTOC in early times. So the extremal OTOC is an analytic extension of maximal chaos, which is also bounded for real T. Why should anybody care about this extremal solution? There is a reason why this extremal solution can be very important. So one can rigorously show that the extremal solution provides a Callan-Lehman type spectral representation for all OTOCs. So any OTOC can be written as an integral of the extremal solution, which this is the solution that I showed you in the last slide, times some density function rho. And one can rigorously show that this density function rho obeys the following four properties. It's a real function, it's non-negative, it's a smooth function, and it's bounded. The advantage of this representation is that all the chaos bounds in this representation are automatically satisfied. So you don't actually have to do anything else. You don't actually have to check all infinite set of chaos bounds. If you write it in this form, they're all automatically satisfied. And actually, this is in my opinion, this is the right language to actually talk about analytic completions of maximal chaos. To do that, let me note one thing. So in this representation, the extremal chaos is basically a single particle state. In other words, basically the density function is given by this Dirac delta function. Of course, this is in tension with the boundedness property of the density function, as I showed in the last slide. So that means a physical system cannot be exactly extremely chaotic. However, in physical systems, the delta function should be replaced by a smooth but narrow distribution. So it is natural to talk about small deformations of extremal chaos, which are basically where you replace the delta function by some narrow distribution like this. So the density function is zero everywhere other than a small window around some T effective, which is not very different from the scrambling time. So this is how one can define small deformations of extremal chaos. Of course, the profile inside this window can be very complicated, but still the important point is the density function is vanishingly small everywhere else. The reason I'm talking about small deformations of extremal chaos at all is that one can show that all analytic completions of maximal chaos are small deformations of extremal chaos. So that's the main point that I want to emphasize. However, that does not mean the OTOC. However, the resulting OTOC can differ significantly from the extremal OTOC. But when you write down everything in terms of the density function, they must be small deformations of extremal chaos. And this general statement can actually be checked for all the known examples, such as like 2D CFTs with large central charge or the Schwarzian theory. In all cases, you will see that the density function has exactly this behavior. And in fact, not just that, in all known examples, the density function actually has a very simple profile. It only has a single peak, which looks exactly like this. Okay, so now it is natural to, very natural to make a conjecture which follows from the previous observation. We can make the conjecture that all theories of quantum gravity and their holographic duals are strongly chaotic systems that are small deformations of extremely chaotic systems. So this is a very reasonable assumption, reasonable conjecture, which follows directly from the first Kremlin conjecture. Okay, so let me conclude. So the main point that I want to emphasize is the following. A lot can be learned about quantum chaos directly from basic principles and symmetries. For example, I showed that the OTOC must obey an infinite set of constraints in any thermal quantum system with a large number of degrees of freedom. There exists an extremal OTOC, which is a unique analytic extension of the maximally chaotic OTOC, saturating all the chaos bounds. The extremal OTOC provides a Callan-Lehman type representation for all OTOCs. And in my opinion, this is the right language for studying quantum chaos. Finally, I argue that all analytic completions of maximal chaos are small deformations of extremal chaos. And this should be of importance in quantum gravity. Thank you for your time.
Okay, thank you, Sandipan, for nice talk. Let us have a few questions. I think I can see the hand of Navamita, Surabhi, and Abhijit in that order, and one more. So, Navamita, please start.
Yeah, thank you, Sandipan, for the nice talk. I have one question. So, I understand even from your last slide that there are infinite set of constraints that need to be satisfied, right? So, can you just tell me, like, when you got this extremal chaos condition, then how you made sure that all these infinite set of constraints were saturated? I mean, exactly how you reached to that condition of extremal chaos?
It's basically, yeah, so there are infinite set of constraints, and
maybe you can go back to your extremal chaos slide.
Probably this is.
Go back, I'll tell you.
This or this one, you mean?
This one, yes, exactly, yes.
So you have if I understand correctly, your question is how do I get this OTOC?
Because you are supposed to satisfy infinite set of constraints, right?
Exactly. So, yeah, so it's that's why it's kind of surprising. Like you can actually write down all these constraints, like as I showed you in terms of the moments, and from those constraints, you don't even have to actually assume anything about the functional form of the OTOC. So the structure of those constraints are such that you can see that after some, like you can see that like there is a very non-trivial way to saturate all of them. Like,
sorry, my confusion is this: when you say that you are writing down all those constraints, you mean up to certain term only you are writing down, right?
No, these constraints are completely non-perturbative. So by constraints, I mean like the constraint in terms of the moments, like they are completely like they don't care about.
Okay. Then you have infinitely many, no? So
yeah, even then, like for example, like the log convex is kind of difficult to actually derive. Yeah, so, but let me give you the gist.
Okay.
So since as you can see from this expression, this is the only constraint that you can actually saturate. It's the log convexity condition, and whenever you have a condition like log convexity condition, its saturation is actually very easy. It gives you a function in term as a function of J. Okay. So what you end up with is basically, if you saturate this, you end up with a moment as a function of J with some unknown function of time, which is an overall factor. Okay. So then without actually going into detail, so these moments actually, by definition, they satisfy some differential equations. So when you make sure that the thing that saturates the lock convexity condition obeys that differential equation, it basically gives you the undetermined function of time.
Okay. Thank you, Shanti.
And all these conditions that you have to actually, you cannot saturate, but you have to satisfy. They are basically like, there will be some constants in those expressions, and you have basically can pick the sign of those constants. That's it.
Okay. Thank you.
There is a very easy, like in my paper actually I showed it. There is a very easy way of deriving it. It's not actually very complicated.
Okay. Thank you.
Hi, Sandipan.
Hi.
Yeah, thanks for some very interesting. Thanks for some very interesting results. So I wanted to know. I mean, it should. You must have thought about how to generalize it for rotating systems with different left and right temperatures.
I haven't, but like the way these constraints are derived, they require so little information about the OTOC. Like these kind of constraints, they are very general. So it's more like the way you can think about them is basically this is kind of complex analysis result. So if you can make sure that whatever quantity you start with, they satisfy all these properties of analyticity, boundedness, and source reflection. These constraints, they're always true.
Okay. Yeah, it will be nice to see the kind of function that you've written, the closed form, later in the next slide, to see it also for that case.
Only non-trivial thing that might happen, I got kind of lucky to get a closed form answer for the saturated OTOC, but it's completely possible that the final answer might not even have a nice form.
Okay, thanks.
Yeah.
Now, Abhijit, can you ask your questions?
Hi, Sandipan. Fantastic talk.
Thanks.
Especially the part about this spectral representation is very interesting. So could you tell me a little bit about if there is any physical understanding of why this should be thought of as a spectral representation? Is there an underlying Hilbert space? Or is it just the mathematical property that the density function should obey all the density function-like properties?
I can give you two answers. One is basically even when I call it it's a current element type representation, it's not, because it's an integral over time, not energy. So the reason I call it a density function is basically because it's a positive function and it has all the properties of density function. But I can tell you one observation that that can support this kind of interpretation. So what you can do, you can just map this. You can just take this expression and you can just map time to energy and scrambling time to something like chemical potential, things like that. So then this F extremal will turn out to be exactly the Fermi-Dirac distribution. In terms of if you just substitute T by A, things like that. And they are basically you'll have an integral of the Fermi-Dirac distribution with rho of some E. So just by and it's kind of amusing why the Fermi-Dirac distribution emerges from this, but it's exactly the Fermi-Dirac distribution.
Okay, I see. And would you say that if this density function it does not satisfy any of these properties that a density function should satisfy, then this kind of a OTOC should be ruled out?
Yes, exactly.
So there is a precise if and only if statement that the inequalities with 1, 2, 3, 4 here.
Exactly. So the statement is the following. So I derived all this that there are infinite set of constraints. So those constraints can only be satisfied if these four conditions are true. If and only if.
If and only if. Okay, nice. Thank you.
Okay, the next question is from Deepan Betal.
Yes, sir. Am I audible?
Yes.
So in the OTOC, the V and W functions, can they be related by some kind of Lanchas algorithm?
You mean like in the definition of the OTOC?
Yes, sir.
Yeah, that doesn't matter for me at all. Like as I discussed, like it does not even matter what the only thing that I use is the fact that they are Hermitian operators. That's it.
Okay, sir. And sir, in the graph of the scrambling time and the dissipation time, if we consider Hawking radiation, would that have any kind of relationship with the page curve?
That's a good question. So I don't know the answer, but the extremal solution, the extremal OTOC that I wrote down, that might have something to do with the information paradox problem. The reason I'm saying that is the following. So in terms of the OTOC, the information paradox problem is basically the fact that at long time, it seems like the OTOC will go to 0. But we know that it cannot go to 0. It should be non-zero but small. And this extremal OTOC is the only example I know of which actually goes up at late time. All the known examples, such as the Sorgian theory, or if you even if you take 2D CFT with large central charts, the OTOC always goes to 0 at late time. So I'm just speculating that this extremal solution can have something to do with like things like information paradox, page curve, stuff like that. But yeah, again, these are all speculations.
Okay, thank you, sir.
Okay, so I think we should conclude this talk by Sandipan. Very nice one. So next speaker is Pratik Rath. So he will be speaking on the page curve for reflected entropy.
Thank you so much for the invitation. I'd like to tell you about this paper, that one of which came out a few hours back, and one more that should be out soon. For those who've seen a version of this talk before, hopefully there'll be some new things that you'll learn from this talk as well. Okay, so let me get started. So the motivation behind this work was it was part of this goal of trying to understand the emergence of geometry from entanglement, the program which we like to call 𝗰𝗵𝗶𝗶. And the sort of gold standard of this program has been the Ryu-Takayanagi formula. So the Ryu-Takayanagi formula tells us that the entropy of a boundary subregion, which I have taken to be these two intervals here, is given by the area of the extremal surface that's anchored to the endpoints of the boundary subregion, divided by 4g Newton. And there's been a lot of work trying to generalize this beyond just the area term. There are quantum corrections that become important, and this has been very fruitful in understanding things like the page curve for entanglement entropy. And so part of the goal that we had was to be able to understand other such holographic connections. For example, the extremal surface has this nice connection to the entanglement entropy, but you might ask about the areas of other such bulk surfaces, which are, say, non-extremal surfaces. And also, in order to understand the entanglement structure better on the side of the boundary, we'd like to understand some other quantities. So, for example, the entanglement entropy is only a good measure of bipartite entanglement in pure states. However, in general, you can have multi-party entanglement, and that can play an important role in the emergence of geometry. And so what we'd like is to have more such entanglement measures that we can understand better, and especially if they have a good holographic dual. So with that, let me tell you about the reflected entropy, which is one such measure. So the reflected entropy is defined by considering this canonical purification. So we start with the density matrix, which is in general a mixed density matrix on systems A and B. And we purify it in a very particular way. So we consider the matrix, the density matrix, and take a square root of the density matrix. This gives us an operator that acts on the Hilbert space of HA tensor HB. And now we think of this as a state which lives on a doubled Hilbert space, which consists of HA tensor HB, which was the original copy, as well as a reflected copy, which is HA star tensor HP star. This is perhaps something that's familiar to people in the example of going from the thermal density matrix to the thermophile double state, which is the canonical purification. So this is just a generalization of that procedure. And then having done so, we define the reflected entropy as the entropy of the region AA star in this particular canonically purified state. So just in pictures, we start with a state which consists of our regions AB and perhaps some purification C. We trace out the region C and then consider a purification where we just double the state on AB. This gives us this region AA star, and then computing the entropy of AA star gives us some measure of the correlation between the region A and B in the original mixed density matrix. Okay, good. Now, this particular measure has the nice feature that it has a very good holographic dual. It was proposed to be a sort of generalization of the Ryutakyanagi formula, which involves the so-called entanglement wedge cross-section. So when you compute the reflected entropy of two boundary regions, A and B, which I've taken to be two intervals in this picture, the proposal is that one minimizes over possible cross-sections, which is this red line here, and minimizes them over all possible ways of splitting the entanglement wedge into two parts. So you split it into a part that's homologous to A, and there's a part which is homologous to B, which I've called little b. That gives us, that corresponds to this area term. And then there are, as usual, quantum corrections coming from bulk entropy terms. This was discussed in this set of papers. Why should you believe something like this to be true? There's a simple heuristic argument for this, which is that we can consider a geometry which consists of two copies of the original region. So when we consider region A and B on the boundary, the bulk dual of this subregion is just the entanglement wedge, which is the region shaded gray here. And naturally, when we do this process of reflection, we just consider a doubled copy and then glue them together at the Ryutakyanagi surface. This gives us a spatial geometry which looks like this cylinder with A and A star on one side and B and B star on the other side. Once you believe that this is the bulk dual to the canonical purification, then the entropy can just be computed by the Ryutakyanagi formula. And then the entropy of AA star is just given by two copies of this entanglement wedge. So that's sort of the motivation behind considering this quantity. Now we.
Sorry, I have a question. What if you're below the phase transition? What if AB is small? That what happens then?
Yeah. So thanks for that. So if you're in a disconnected phase, so let's say the intervals are small, then there's no entanglement wedge cross section because there's no surface needed to split them into two parts, and so the reflected entropy is just zero. The entanglement wedge cross section is trivial.
Okay, thank you.
Good. So we can work this out in a little bit more detail beyond this heuristic argument by doing a replica trick. So firstly, in order to do the replica trick, one needs to construct the canonically purified density matrix, which consists of the square root. The square root is hard to construct in general in a path integral. So the trick that we employ is to consider the state, which is rho to the m over 2. If we take m to be an even integer, then this can be constructed using a path integral. And then eventually we would like to analytically continue this parameter m to 1 to get the square root. Similarly, we employ another replica trick to compute the entropy in this state. And that's the more familiar one where we compute the Renyi entropies at integer n and then do some analytic continuation to 1. So in the end, what we want to do is compute this quantity and analytically continue both the parameters m and n to 1. This gives us the reflected entropy. This is something that one can set up in gravity. And the naive guess, which was part of the original proposal, was to do a sort of saddle point approximation similar to what Lukowitz and Maldacena did for the entanglement entropy. However, there are some issues with this proposal. This analytic continuation firstly suffers from an order of limits issue, note that we have these two parameters that we want to analytically continue to 1. And depending on how you do this analytic continuation, you get different answers. This was pointed out in this particular paper. And so it wasn't clear that there's a principled reason to consider one particular choice of analytic continuation and how to see that it gives the physically correct answer. So that was one issue. And further, as Sukrut just asked, which was when you have a phase transition in the entanglement wedge, the reflected entropy suddenly jumps from a value that's 0 to a value that's non-zero. So there's a very sharp discontinuity in the value of the reflected entropy if we believe the holographic proposal. This indicates that there are non-perturbative effects that are important near this phase transition. And so one would also like to get some handle over such effects in the path integral. And so overall, we need a better calculation in some toy model to be able to understand this issue. Okay. So the toy model that we work with is the so-called West Coast model. This is a toy model that was developed in this paper, which consists of a simple model of J-Teitelbaum gravity, which is 2D gravity, coupled to end-of-the-world branes. So we have an action which has the JT action, which consists of a topological term with parameter S0, and the usual JT action with a dilaton that's coupled to the metric. And further, we add in this term, which is a brane tension mu. And the Lorentzian solutions to this action look like the following. One has a 2D black hole with some horizon and these end-of-the-world branes. The end-of-the-world branes are chosen to have some flavor indices that live on the brane. It's some sort of global symmetry. And we choose to entangle these flavor indices with some auxiliary radiation system. So here we've taken the radiation system to consist of two sets, R1 and R2. And R1 and R2 are entangled in this particular way. So the overall state of the system is such that we consider the black hole in a state with flavor indices ij on the end of the world brane, and the indices I and j are entangled with the radiation systems R1 and R2. The number of flavors are K1 and K2, and the product K1, K2 is represented by K. So the parameters in this problem are essentially the number of flavors, which denotes the entanglement with the radiation system, as well as the black hole entropy, which is basically the area of the horizon. This can be thought of as a model of a partially evaporated black hole. So you can imagine allowing a black hole to evaporate partially, stopping the evaporation at some point. And then what you have is some radiation in the exterior that's entangled with its interior partners. And so this is some sort of toy version of that picture. Okay, so now in this model, the page transition is basically the fact that we can tune the parameters that denote the amount of entanglement between the radiation and the end of the world brane, which is this log K, to be more or less than the black hole entropy. When it's more than the black hole entropy, this is what we indicate as post the page time. And as is familiar from the work that's happened over the last 2 years, there is a geometric description of this, which corresponds to the entanglement wedge, including an island. So when we look at the regions R1 and R2, they have an island that consists of the interior of the black hole, which gives you the page curve. Now, what does this mean from the perspective of the canonical purification? For the canonical purification, it indicates there's a qualitative change that happens, as we discussed in the case of the two intervals. Before the page time, the entanglement wedge is trivial. And so when we purify the state on R1 and R2, all that ends up happening is that R1 is entangled with its doubled copy R1 star, R2 is entangled with its copy R2 star, and there's no entanglement across these. So if we compute the entropy of R1 star, it's 0, because there's no entanglement across this cut. However, when we cross the page time, then now there's an island for R1 and R2. And so when we consider the doubled copy of this entanglement wedge, it includes a closed universe. This closed universe is made of 2 copies of the island that are glued together at the horizon of the black hole. And now, when we compute the entropy between R1 and between R1 R1 star and R2 R2 star, it's non-trivial. Depending on how we tune the parameters, there are 2 possible so-called RT surfaces in this picture. It's either the orange lines or the pink lines here, depending on whether K1 is less or K2 is less. So in the end, the entropy turns out to be twice log of K1 or log of K2, whichever is minimal. And as expected, we see a sudden jump from 0 to a finite value as soon as you hit the phase transition. This is what the holographic expectation is. And we wanted to analyze this in a little more detail by understanding whether this is really the correct answer. The way we do this is by doing a more refined sort of replica trick, which is called the resolvent trick that was introduced in this paper by Pennington, Schenker, Stanford, and Yang. So we consider the resolvent, which is this function that can be thought of as the generating function of pars of the density matrix. And by the pars of the density matrix can be written down as boundary conditions with integer number of boundaries. And then the rules of the path integral tell you to fill these in with some geometries that are consistent with the boundary conditions. Now, similar to what one does in quantum field theory, you can write down this resolvent in terms of its connected part, which we denote by F, which is similar to what you do with 1-pi diagrams in quantum field theory. And F can be written as a sum over geometries that are connected in this particular way. So you can have 1 boundary geometries, 2 boundary geometries, and so on. Once you do that, what we see is that we've now managed to write the resolvent in terms of a function of the resolvent. So it's a self-consistency equation or a Schwinger-Dyson equation, which you can solve. And this was solved in the original paper to find an approximate entanglement spectrum. The approximate form of the entanglement spectrum is simple. It essentially takes the form of a cutoff thermal spectrum. You take the thermal spectrum, look at its first k eigenvalues, and cut off the spectrum at that location and shift it appropriately to make it correctly normalized. The details of this are not so important, but the important fact is that solving this resolvent trick gives us the entanglement spectrum. Now we can do the same thing for the reflected entropy. So we consider the reflected entanglement spectrum, which is the spectrum of the density matrix rho R1 R1 star. The way we do this is by generalizing the resolvent. We consider the state rho to the m over 2, which was prepared by some path integral for even integer m. And then we do this thing where we flip Bras to Ket. So we consider a state that's prepared here, and then its Hermitian conjugate. By tracing out the R2 R2 star legs, we end up with the density matrix on R1 R1 star. In short, what ends up happening is that a particular component of this resolvent gives us the correct resolvent for the density matrix. Now, I can't go through all of the details, but just briefly to mention what we end up doing is that there's a diagrammatic summation over a class of planar diagrams. So you get some boundary conditions for this resolvent. You can look at all possible geometries that fill in those boundary conditions. And we can classify them based on their weights. And there's a particular class of planar diagrams that we conjecture will dominate. And these include a lot of replica symmetry breaking effects. So they have, there's a particular class of saddles which are important. There's evidence for this class of diagrams by looking at certain asymptotic behaviors. And also we have evidence from numerical calculations, and also similar effects show up in our tensor network calculations, which you can find in the paper that appeared today. And so there's a significant amount of evidence for this being the correct resummation. Once you do that, then you end up with a solution to this Schwinger-Dyson equation, which you can solve self-consistently. And you end up with a simple entanglement spectrum. So let me just explain in detail what the spectrum turns out to be. The spectrum has a simple form where it has 2 main features. So the spectrum has one pole, which is a single eigenvalue. The single eigenvalue can be thought of as corresponding to the disconnected sector. So when we are far into the disconnected phase, we end up having a geometry that just corresponds to R1 being purified by R1 star, R2 being purified by R2 star. And since there's no entropy, you expect it to be a single eigenvalue since it's a pure state. That's this feature. On the other hand, there's another feature, which is a mound of eigenvalues, which has a number of eigenvalues that's roughly k1 squared. And it's a very sharp peak. And so when you compute the entropy for this mound of eigenvalues, you'd get something which is twice log k1. This is the answer you'd expect in the connected sector. So in the connected sector, remember that there was this closed universe, which was causing it to have a non-trivial entanglement across the R1 star cut. And it gives you precisely this answer of 2 log k1. However, what we find here is that this was true far on either phase, but here we see that these two features persist no matter where you are in parameter space. All that changes is the weights, which we've denoted by PC and PD, the probability of being disconnected or connected, which interpolate across the phase transition. So depending on these weights, we get a reflected entropy that's basically given by the probability of being connected times the answer in the connected phase. So all I need to tell you to explain the phase transition is what these probabilities do. The probabilities can be computed analytically in terms of the Renyi entropies of these systems. Q here denotes some parameter, which essentially tells you on which side of the phase transition you are. So as you increase K, Q increases. And so you're far on the connected side of the phase transition, whereas for small k, for small q, you're on the disconnected part of the phase transition. The transition happens exactly at q equals 1. So if you look at this plot, what you see is that the probability of being connected is really small for small q, and it increases around the time when the phase transition happens, and it becomes 1 at large q. Now, what I've plotted here is two different curves. The red curve corresponds to the microcanonical ensemble, where the energy of the black hole is fixed. And this gives you a very sharp transition. However, the blue one corresponds to the canonical ensemble, where you have thermal fluctuations. And since thermal fluctuations basically tell you that there are fluctuations in the horizon area, the transition happens at different locations depending on which area you're at. This has the effect of spreading out the phase transition over a large region. And so this is similar to what was found in the case of the page curve for entanglement entropy. So we find something that's very consistent with this proposal. Now, we also consider the Renyi versions of this reflected entropy. And the Renyi versions show a novel feature. The novel feature is that the phase transition shifts depending on this Renyi parameter. The location of the phase transition depends on this Renyi parameter m. For m greater than 1, we're essentially considering temperatures that are slightly lower than the temperature of the black hole. So the area is smaller, and so the phase transition happens earlier. So at a smaller value of k, you see these thicker curves which undergo these transitions, and this corresponds to m greater than 1. For m less than 1, we find that the phase transition happens later, and this is expected because m less than 1 corresponds to weighing the higher temperatures more, and hence the phase transition happens later. But as an aside, in order to do this calculation, we had to compute the Renyi entropies in this model. And there's an interesting feature that for m greater than 1, one finds a nice 𝗰𝗫𝘀𝗀𝗃-like formula. This was something that was proposed by Zhidong about 5 years back. However, for m less than 1, there's no analog of this 𝗰𝗫𝘀𝗀𝗃-like formula. And you find large corrections over a large region of parameter space. This is something that I think should be explored more in future. Okay, so with that, let me summarize. The gist of the talk was that this proposal that the reflected entropy is equal to twice the entanglement wedge cross section works in this toy model. There were various issues with this proposal that were hard to handle in situations where you can't do the gravity path integral completely. And in this particular toy model, the fact that the Joydeep-Teitelbaum gravity path integral can be done explicitly helps us understand a lot of these issues. So having demonstrated that this holographic proposal works well, we can also understand better the procedure for analytic continuation. The analytic continuation that gave rise to this entanglement wedge cross-section proposal was, we had these two parameters, n and m, and what we had to do was analytically continue n to 1 first and then m to 1. And in this model, there's a good reason for this, and we can show this explicitly. And the resolvent trick resolves this issue. Further, we found that there were these fluctuations near the phase transition because of replica symmetry breaking saddles, which gives some important non-perturbative effects. This smooths out the page curve for reflected entropy over a large region. And we expect that similar features should show up in other examples in ADS. So when we have two intervals as well, there's this phase transition, which goes from the disconnected phase to the connected phase. And we expect such thermal fluctuations to be important there as well. There's a similar calculation that we did in tensor networks, which you can find in the paper that appeared today. And there we find similar features, but there's also a richer spectrum. So there's more things we can do in those models, but the story overall remains quite similar. So with that, I'd like to thank you.
Okay. Very nice talk, Pratik. You also finished in time, actually. So we have about 5 minutes for questions on this talk. Yeah. So we have Sukrut Raju. Yeah, your hand raised.
Hi, Pratik. Thanks for the nice talk. So I had a slightly tangential question. So in this model, this model is kind of an unphysical model, right? Because you have these flavor indices on the brain that don't actually interact with gravity. So I understand you can define the model well by just thinking of a Euclidean path integral with decorated boundaries where you add some flavors. But I mean, do you have any feeling for how these calculations would change if you made it more physical by really adding interactions between these degrees of freedom on the brain and the ambient space? I mean, would that change anything, or do you think that might be important?
Yeah, that's a good question. So I think like qualitatively, at least for the calculations we did, I don't think much will change. For example, in the case of the entanglement entropy, there were these questions about this same issue that you talked about. There's a global symmetry of these flavors on the brains. And there were some papers which did calculations which refined that, and they basically found the same sort of page curve, and nothing much changed in that context, at least. So I expect that for the reflected entropy as well, the calculations will go through in a similar way. But of course, it's a good question. Like I would like a more realistic model where we can do this calculation explicitly.
Yeah, there is another question from 𝗦𝗵𝗶𝗶𝗶.
Hi, Pratik. Thank you for the nice talk. Quick question: do you imagine one could like consider multi-party entangled states of like the CFT dual itself without having this radiation sort of bath lying around? And would you think that sort of gives a more like a physical entanglement, like a geometric entanglement wedge cross section in these models, as opposed to having like lines cutting through this? Is there some way to like have a geometric cross section in these models?
Yeah, in 2 dimensions, I don't know exactly how to do it. At least in Joydeep-Teitelbaum gravity, I don't know of a situation where you have an island and it gets like. There's a slightly refined version of this, which is the East Coast model, where you have Joydeep-Teitelbaum gravity coupled to like flat space. There you do find this feature. It was pointed out in this paper by myself, Masamichi Miyaji, and Ben Chandrasekharan. So in that context, even though it's not exactly an answer to your question, because you still have this auxiliary bath region, but you do end up getting a geometric cross section. So you have an island, and there's a geometric cross section at the middle of the island. So that's a slightly better version of this. But yeah, maybe in higher dimensions with something like a doubly holographic model, you'd find something like a geometric cross-section.
I see. Thank you.
Thanks.
Okay, so I think there's no more hands raised. I have a very trivial question. That you are calling this reflected entropy. In what sense this is reflected? You have a system A and they are sort of disconnected on boundary, but why you call that reflected? I mean, this would be a joint entropy, you know, which is the entropy of both system A and B, you know, which are disjoint in some sense.
So we could have done something like, we could have taken like one of the regions A and computed its entropy. That would be a different measure of entanglement. The reflected came from the fact that because we had a mixed state, we traced out the C, and then we reflected it to consider this other copy, which was A star and B star. So the reflected was just saying that the reflection was part of the purification that we used to define this entropy. That's all that the definition meant. Like even here, like geometrically, we see that we have this single model where we have one copy of this wedge, and the reflection indicates that we just get this doubled copy where we glue them together. The reflection is just, it's this conjugate symmetry.
So is the way of integrating out your C from the from your entanglement wedge of the two.
Yes.
Yes.
Sorry, I missed the last part.
Okay, so I think there is one more hands raised by Deepan Betal, please. Go
Yes,
ahead.
sir. Yes, sir. Am I audible?
Yeah.
Yes, sir. In the entanglement wedge figure over there, we can consider C as a bath, right?
In this figure, you mean?
Yes, sir.
Yeah, you can think of C as a bath if you like. Yeah, it's basically what's purifying the state on A and B. Yeah.
Okay, sir. So if the Hawking radiation interacts with the bath, will that cause any kind of change in the area of the entanglement cross section of AB?
Sorry, in this model, I mean, in this picture itself, I was just considering pure ADS. There was no Hawking radiation here.
In the case where you have the island and we.
In the case where the island, yeah. So in this example, we were considering, like, this is probably related to Surat's question, like we were considering a very simple model where there were no interactions. All we did was we assumed there were some interactions that led to this entangled state. So there was some process which generated this Hawking radiation. And then we were just looking at the entropy at this fixed time. Like there was no dynamics. But in order to generate the state, there must have been some interactions that led to this. So it's sort of secretly hidden in this original state that I talked about.
So if we take different instances of time, could that expand the entanglement wedge and hence changing the eigenvalue spectrum we had shown with the pole?
This one, sorry, this one?
Yes. Could that expand the one of the connector region? Of the connector region, could it expand it a bit if we check at different times?
Qualitatively, like as long as you're at late times and you have an island, you'll be in this connected phase, even after time evolution. And the dominant thing will be this mound of eigenvalues. If you're pre-page time and you don't have an island, then you're right that this thing will dominate.
Okay. Thank you, sir.
Okay, I think there is one more question from Arnav, maybe shorter one. Yeah, please.
Hi, yes, I'll just ask a very quick question. First of all, thanks a lot for a very nice talk. So my question is, instead of considering, doubling the system, you could have considered n copies of this, right? I mean, and of course, it will get into this multipartite entanglement and so on, about which very little is known. But I'm just wondering whether that's a useful way to think about it.
Yeah, we could. Actually, there are such measures that have been considered. So people have talked about these generalizations of the entanglement wedge cross section, which are supposed to correspond to. So you start with some many party system and then glue them one by one in some very complicated way. that gives rise to these like tripartite and four-partite cross sections. But the problem is we still don't understand the boundary dual of these things. So it would be nice if we can construct some boundary dual, which was nice. Like in this context, the reflection was sort of unique. Like we just took this density matrix, and the density matrix has a natural purification on a doubled copy. But maybe there's some other complicated thing you can do where it becomes on n copies and then compute some other entropy.
As you said, it's probably not unique. There could be many embeddings and so on.
Yeah, but if like in this case as well, like the purification aren't unique, but there's something nice about this particular purification. So maybe you could, in the n-party case, also find something that's consistent with, say, some permutation symmetry of the systems or something like that, and that might be unique. I'm not sure.
Okay, thanks a lot. Thanks.
Okay, so let us thank the speaker for very nice presentation. Our next speaker is Joydeep Chakravarty.
Hi, thank you. Should I share my screen?
Yeah, please share. Yeah. Okay, so he is speaking on toy model for bags of gold and monogamy paradoxes. Mr. Jaydeep Chakravarty, please go ahead.
Yeah, good morning, everyone. And thank you, organizers, for inviting me to this conference where we have seen many fantastic talks over the past few days. So today I'm going to present my recent work on aspects related to black hole information. The title of my talk is Toy Models for Bags of Gold and Monogamy Paradoxes. And this is based on a paper, this is based on two papers, basically one on this overcounting of interior excitations and another on monogamy paradox with Tunir and Priyadarshi, who are two junior graduate students at ICTS. So the broad theme of this talk is the underlying theme of this talk is to pose these paradoxes using bulk effective field theory and to precisely understand what goes wrong while using such a description. I'll shortly motivate and describe these paradoxes and also describe possible resolutions in my talk from the bulk perspective. So let's start with the discussion of the bags of gold paradox. So let me briefly outline what we are going to look at in this part. So the paradox is basically the fact that certain space-like slices, for example, Hartmann-Maldacena surfaces, which go inside the black hole interior, become very large in volume at late boundary times. And these large volume slices can host a considerable number of semi-classical excitations, which is far higher than what the Bekenstein-Hawking entropy suggests. And this is known as the bags of gold paradox. Now, our proposed resolution is that these interior excitations, these bulk interior excitations are really overcounted. That is, semi-classical bulk states placed far apart from each other in the interior are seemingly orthogonal. However, these states have small but significant inner products between them, which deviates from the semi-classical expectation of zero inner products. So roughly, the situation is something like this on the right-hand side. So this is our eternal Schwarzschild black hole, and we have a Hartmann-Maldacena slice at some boundary time t, and we have placed these excitations, excitations far apart from each other. These bumps denote these excitations, and these are placed far apart from each other in the interior. So one can keep on adding a large number of these excitations and overcount this Bekenstein-Hawking entropy. So how do we place these excitations? So first, let's discuss what this slice is. So we are interested in the maximum volume of slices which end at u0, 0 on the left horizon and 0, u0 on the right horizon. And the volume of these slices grows proportionally to log of u0. The excitations are placed on these slices by acting with unitary operators on the right CFT in the thermofield double state. So these states are constructed using the state-dependent formalism of Sukrut and Kyriakos, where this U of t is basically a unitary operator acting on the right CFT, and HR is the right CFT's Hamiltonian. Now one can place multiple excitations in a similar fashion. So So one can place multiple excitations in the similar fashion due to the fact, by utilizing the fact that the time-like coordinate t in the exterior becomes a space-like coordinate in the interior upon the propagation of these excitations. So we can create another excitation in the interior of this particular form, psi2, where the action of the Rindler Hamiltonian using factors of e to the power plus minus I HRT spatially separates this first excitation from the second one. And since the exterior time-like coordinate becomes space-like in the interior, these excitations are placed far apart from each other if T is large enough. We can generate m number of such excitations similarly and arrive at this particular picture of m excitations in the interior. So to work within effective field theory, we'll generate these excitations with small back reaction. For k excitations, we'll ensure that the number density of excitations, rho, which is simply k divided by the volume of this slice, is finite in the thermodynamic limit, that is with k and v large. And this allows us to calculate the entropy of these EFT excitations by treating the system as a dilute gas of excitations living on the slice. So the expression for the entropy is just given by S is proportional to the volume, where we have calculated this using the standard microcanonical ensemble trick by utilizing the fact that this system is a dilute gas of excitations. And we know that this volume grows proportional to log of U0. So really this entropy grows proportional to log of U0 as we go to later and later times. And this gives rise to the paradox. So our proposed resolution is that even though we have constructed these excitations to be in such a fashion that they are spatially separated far apart, there is small inner products from this. There are small inner products between them. So let us understand this thing in detail. So the paradox arises due to a huge overcounting of this bulk Hilbert space. In semi-classical gravity, the inner product between two bulk states is given by an exponential. So if you take the inner product between two different bulk states, this has an exponential factor of e to the power minus n times v, where n is just the central charge of the associated CFT, or it can be thought of as 1 by g Newton. And v is the phase space separation between these two metrics. However, this description is really misleading when the phase space distance between the between the corresponding classical configurations is very large. In particular, when the distance is very large, we expect that the inner product between these states go to 0. However, the inner products do not really go to 0, but develop a saturated fat tail of order e to the power minus n. So this really is the motivation for our proposal, and consequently, this explains why the excitations are not really independent. So let us count how many bulk excitations can we fit using a smaller Hilbert space. So consider a Hilbert space of dimension n, and our problem is to calculate what is the maximum number of vectors m which satisfy the following relation. That is, these vectors are normalized and they have a very small inner product between each other, which we quantify by saying it's of the order epsilon. Now, what is the solution to the problem? The solution is that unit vectors in this Hilbert space live on the surface of a 2n minus 1 dimensional real sphere, and one can estimate the total number of these vectors by dividing this 2n minus 1 dimensional real sphere surface area with the area of an exclusion zone. So what is this exclusion zone? The exclusion zone is basically the fact that if we have a vector vi, so if we try to put another vector vj which is very close to this vi, then this second condition in our problem will be violated. So really there is a exclusion region around this vi in which no other vector can exist. And so we are dividing this surface area of this 2n minus 1 dimensional real sphere with the area of this exclusion zone, and using this we can find that the maximum possible vectors for a small epsilon goes something like n into e to the power n epsilon square by 2, which is really a very large number. And this is how we think that all these bulk excitations are really encoded in a smaller Hilbert space. and this is why we think that this entropy is really correctly counted by the Bekenstein-Hawking entropy. But in the using semi-classical, using effective field theory, we have a higher number of, we have a seemingly larger entropy than the Bekenstein-Hawking entropy. So we performed some checks for this. So we also showed that there is no paradox in the CFT using our form of interior, using the form of interior excitations that we considered, that is these kind of interior excitations. We showed that there is really no paradox in the CFT. And we also posed the paradox for single-sided pure state black holes and demonstrated why there are small inner products between candidate interior excitations of order e⁻⁻n. And such excitations lead to qualitative and quantitative differences in the spectral or observables like level spacing distribution and the spectral form factor as well. And within small n matrix models, we demonstrated how candidate interior excitations can again lead to an overcounted Hilbert space. So before I go further, are there questions regarding this?
Hi. Yeah. Small question. So on the previous slide, the estimation is n times e⁻n⁻ square/2, right?
Yes.
And now the proposal is that epsilon is what, e⁻n capital N?
Yeah, the inner products are of this particular order. Yes, there is a fat tail of order e⁻⁻n.
So it's not too much, right? So how do you explain? I don't know.
Oh, no. So the point is like even a very small difference in this between this n and and epsilon can lead to, see, this factor is really exponentiated. So if n into epsilon square is a small quantity, then this will be exponentiated, right?
I mean, e⁻0. I mean,
no, it's not exactly 0. That's the point.
Yeah, but not too much, right? I don't know the orders, how much you have to explain, but it seems that it's not too much.
Well, even if let's say if this saturated fat tail has some if this order e⁻⁻n is some e⁻⁻delta, and the actual dimension is some e⁻n. So if delta is less than 1, this becomes a large number, and this in addition to that, you are again exponentiating that. So it's really a large number.
Okay.
Abhijit, just to be clear, n epsilon square can be very large.
That n, that small n, his thing should be thought of as capital N itself, right?
Yeah. So that small n,
yes.
And I notation, but small n is a number of states, but n epsilon square can still be very large, even if epsilon is small, as long as epsilon is larger than 1/√n. So if epsilon is 1/n⁴, this becomes m can be much larger than n.
Yeah, but epsilon seem to be of order e⁻n or something. Or
no,
not?
so no. Epsilon is not of order. I think this n, I'm confused in notation, but epsilon is of the order of is larger than 1/√√ of small n in this notation. If I understand correctly, Joydeep can correct.
Thank you.
Is that Joydeep?
Yeah.
No, I mean, what is this here? Order of e⁻n in the next slide.
I think small n is e⁻⁻. Small n is e⁻⁻
capital N. Yes.
Yeah, okay, thank you.
Yes. Okay, so I'll move on to this toy model of monogamy paradox. Then, so the goal here is to investigate a toy model in empty flat space, which captures essential features of the monogamy paradox for old flat space black holes using a clean calculation framework. And in general, there exists no nice way to calculate entanglement measures in the bulk from the perspective of bulk gravity. However, we can formulate the monogamy paradox in terms of monogamy of CHSS correlators, which we use to quantify monogamy of entanglement. So let me briefly describe what is this monogamy paradox first. The monogamy paradox within effective field theory is the statement that ingoing and outgoing pair-produced Hawking quanta are maximally entangled, and thus the outgoing Hawking quanta cannot be entangled with other escaped Hawking quanta. So we are making a toy model in order to analyze this paradox. And within effective field theory, we show that the entanglement of approximately local bulk modes just outside the light cone, which is this region B, with the entanglement of this region with modes just inside the light cone, which is this region A, as well as with modes situated far away at the past of future null infinity, which is this region C, the entanglement between these three regions give rise to a order 1 violation in the statement of monogamy of entanglement. And this is the paradox which we are dealing with. So here these regions A, B, and C are spherically supported. So let us understand the monogamy of entanglement, the statement of monogamy of entanglement first. So we start with the construction of a CHSS operator in quantum mechanics, which is essentially a convenient way of understanding Bell inequalities. So to do this, let us consider two sets of operators A's and B's, which are defined such that their operator norm is less than 1 and they commute. And the CHSS operator is this combination of these operators A's and B's, where for classical observables, the CAB is bounded by 2, whereas in quantum mechanics, CAB can violate this 2, but it has an upper bound of 2 root. Similarly, one can again construct another set of operators is C1 and C2, which satisfy this operator norm is less than 1, as well as it commutes with the other operators AIs and BIs. And using this, we can construct another CHSS operator CAC. And the statement of monogamy of entanglement is that this CHSS operator of this AB regions and this AC region squared should be less than equal to 8. So this is a fairly strong statement. In other words, there cannot be a scenario where both systems AB and AC possess a non-classical description. So if CAB is greater than 2, it implies that CAC is less than 2. However, using gravity, we will show that there exists a violation of this statement of monogamy of entanglement in effective field theory, leading to this paradox. Okay, so how do we do this in scalar field theory? The fact that this operators A, B, and C commute is given is same as saying that smeared operators on regions A, B, and C are separated by space-like separated regions. And in general, the global vacuum of any field theory is highly entangled. In particular, the global state for our scalar field theory is a thermofield double when written using Riddler modes. So let us start with the calculation of CAB first. So we can define this operators alpha S, where S is A, where S are the regions A and B using Riddler smearing, and we demand that they are supported in a very small interval near this light cones, near this very close to this light cone. We will need another operator which is the projector onto the SS vacuum, and we can use that to write down these Bell operators in field theory, which are the following combinations. These combinations might look a bit messy, but the point is these operators resemble standard spin operators when expressed in 0-1 basis. So the state here, which we consider here, is the global vacuum state. To calculate the CAB, we first write down these operators alphas in terms of global creation and annihilation modes. And the goal now is to write the CHSS correlator as a function of Bogoliubov coefficients H and G, which we can easily extract. We can easily extract out this Bogoliubov coefficients in certain limits. And finally, we can arrive at this expression for CAB, which is 2.39 using our choice of operators and states, which is greater than 2. So this up to this part is fairly straightforward, that one can calculate this CHSS correlator in scalar field theory. Now we will look at how to calculate this CHSS operator CAC. So the key ideas for this calculation of CAC are as follows. So the first thing is that there is this resheeter property, which is that we can create operators QI with support in the region C, which mimic the actions of BIs or AIs on the vacuum state. So this is the region C, and one can create operators QI, which mimic the actions of these operators BI. Here, S denotes the super translation sector, and however these operators QI are really unbounded. So we need to construct bounded operators CI from QI so that we can use them in CHSS correlations. To do that, we will use the fact that the Hamiltonian of gravity is a boundary term and construct observables using the same. So the observables which we are looking at are the projectors onto the vacuum state. So it was pointed out in these works that there exists a very nice way of looking at these projectors, which is we just exponentiate the ADM Hamiltonian and multiply it with a number and take the number, take A goes to infinity. So if we can also get a better choice of projector, which projects onto which projects below an IR scale delta, and we can use these projectors to construct these CI operators, which are bounded, as well as which acting on the states give us the action of the operators BIs acting on the state. Now, so let me just arrive at the paradox. So so we have constructed out operators CIs which when acting on the state give us the action of BIs acting on the state. So we arrive at the conclusion that this CAC is really a CAB plus some small corrections. However, if we now square these two guys up and add them, it's some 11.4, which is greater than 8. So earlier we had this statement about monogamy of entanglement that the CAB square plus CAC square should really be less than 8. But using this our construction, we have essentially arrived at a order 1 violation in the monogamy of entanglement. So this is the paradox in this context. Now, the resolution of the paradox is that spatially separated observables probe the same underlying degrees of freedom. That is, such observables do not act on a non-factorized Hilbert space. So, one default assumption which went into this kind of a construction was that these observables don't really act on a factorized Hilbert space. We assume that this, since these regions A, B, and C are space-like separated, these can be thought of as a factorized problem, but it's not so. So these circumvents are the conflict with monogamy of entanglement, and the factorization of our theory is Hilbert space on spatial partitioning grounds, which is an implicit assumption, is simply incorrect. This is supported by the fact that if we use the Gauss constraint to calculate BI and CJ, this is not equal to 0 in gravity. Whereas in effective field theory, we will find that this thing is equal to 0, even when there is a phase-like separation. And another way to understand this is as follows. The degrees of freedom in region C already contain information about the A and B regions, which is known as the principle of holography of information. And this is written nicely in this review. So what is the conclusion of our talk? So in our talk, we have looked into two paradoxes from the bulk perspective, the bags of gold paradox, which can be resolved using small gravitational corrections, while the monogamy paradox requires order 1 corrections. Both models demonstrate why effective field theory construction fails to a certain extent and requires us to go beyond the same. The case of bags of gold requires quantum gravity corrections, that is the fact-tail effects for its resolution. In contrast, the monogamy paradox arises due to the assumption that the Hilbert space does not factorize upon spatial partitioning. So, thank you for listening.
Yeah, thank you, Jaydeep, for a very nice talk, and completely in time. So we have 5 minutes for questions and answers on the talk. Is there any question? Any hand raised? Yeah. I see any hand raised by any question on the talk of the speaker?
I have a question.
Yeah, I can see one hand raised by Deepan Beta. Please go ahead. Yeah.
Yes, sir. In the exclusion
Please
region.
go ahead, Deepan Beta.
Yes, sir. Yes, sir. Am I audible?
Yeah.
Yes, sir. In the exclusion regions which you are defined in the space slice, how are the radius of the spheres modified at the boundary of the slice?
You mean in this problem, right? Yes. So here what we are doing is we are counting the number of vectors which have small inner products that can be embedded into a smaller Hilbert space.
Yes.
So there is an exclusion zone because of the fact that we really want this inner product between two different vectors to not exceed epsilon.
Yeah.
If we try to put a vector inside this region, inside very close to this another vector, then this inner product will be violated, right? So that defines an exclusion zone.
Yes.
So what we do is we take this whole real sphere and divide it by the exclusion zone to get a estimate.
Okay, so if we take a space slice and we consider the boundary areas, in that case, how are the exclusion zone?
Oh, I see. So you cannot. So the point is this: that we are not allowing these excitations to be very close to each other. If they are very close to each other, then they will obviously have a larger inner product, right?
Yes. Yes.
So from the boundary perspective, we are sending in this. So in order to construct the initial state, which corresponds to this system, we do not send in these deformations very close to each other. We separate them by large times.
Okay. Thank you, sir.
Okay, so I think there is no more questions, and they were already asked during your presentation. So let us thank Jaydeep again for a very nice talk. And I think this session gets over with this last talk of this session. So I think it's up to, I think Alok is there, and I think Alok will take over from here. Please.
Yeah, so there's thank you, Harvendra. So it seems at least one prediction of mine has come to pass. It was 15, it was 17 yesterday, and it's 20 minutes, 19 minutes worth of tea time. So let's relish every minute of that and resume 11:30 sharp. Is Kamal around? Maybe he will be close to 11:30. So let's resume 11:30 sharp, please. Thank you.
Okay, thank you.
Hi, Kamal, are you there? Can you hear me? Hi, Kamal, can you hear me? No, I cannot hear you. Team, is Professor Kamal audible?
No, he's not.
He's not, yeah. So, yeah, Kamal, there's some audio issue at your end because we cannot hear you. No, cannot hear you. Maybe if there was a provision for you to take out the microphone and just speak without that, or maybe not. Jaydeep is here, right? Jaydeep Kumar Basak.
Yeah, I am.
Okay, so maybe can you can we test your screen share? Maybe you can share your file and go back and forth, see if that works.
Okay, but am I audible?
Yes, you are.
It's okay, right?
Yeah.
Okay, thanks.
Yeah.
Screen share.
Hi Kamal, we can hear you now.
Can you hear me?
आवाज आ रही है.
Can you hear me?
थोड़ा सा ऊंचा बोल लो. Hi Kamal, can you speak up a little, please?
Am I audible?
थोड़ा सा. Can you speak up a little or? Yeah. Yeah, it's fine. It's fine. It's fine. It's fine. Absolutely fine. It's fine. It's fine. It's fine. Kamal, it's fine.
Now they can hear me.
Yeah. Wonderful.
Yeah.
It's so good to more or less see you, Kamal, with all those. You're barely visible. I can understand. I mean, you must be in your JE office.
No, I'm in my office. Yeah.
Right, I can see that. Yeah.
The screen has been shared, right?
Yeah. We need to see your file.
Yeah, this one.
Yeah. Now, yes. Yeah.
Okay. Maybe you can go full screen.
But let me try this one once. Just a second. Is it visible now?
Yeah. Can you go into some presentation mode or full screen or whatever is the equivalent of that?
Yeah. Let me do that. Yeah.
Okay. Just one last thing. Could you please go back and forth? Just go forward and go see. Can you come back? Perfect. Okay. So Kamal, all yours. may I humbly request that we have 25 plus 5 for the 30-minute speakers and 13 plus 2 for the 15, with all questions for the 15-minute speakers towards the end of their respective talk. Right. Thank you so much, Kamal. Thank you.
Yeah.
All yours.
Thank you. Thank you, Alok. Yeah. Thanks. Okay. Welcome to this session. Though I don't see, I saw the speaker. I don't see the audience. Okay. Here we go. Now, the first speaker of this session is Jaydeep Kumar Basak from IIT Kanpur. So he will be talking about islands for entanglement negativity. Basak, Jaydeep, I will get back to you at 11:55.
Okay,
please
thanks.
Yeah.
Thanks. Yeah. First, I would like to thank the organizer for giving me this opportunity to speak here. Today, I will be speaking on Island for Entanglement Negativity, which was done with these people. They were Vinayak, Manshu, and Gautam Sengupta. This will be the rough outline of my talk, where I will try to first speak about entanglement and correlation measures in QIT, then a short review of the holographic proposal, and then the main part, which is the island proposal for negativity. I will again try to sketch some of the double holographic scenarios. I will try to show some of our result, and if time permits, I will go to the replicable part. Otherwise, I will I am going to summarize my talk. So entanglement negativity is a measure of entanglement in mixed state. Let's take a mixed state A, which consists of A1 and A2. In that scenario, Vidal and Warner in 2001, they proposed negativity as a computable measure of entanglement of a bipartite system in a mixed state, which can be written in this specific way. Now, what is this rho A2? To understand that, we can take EI and EJ are two bases in Hilbert spaces, which corresponds to A1 and A2, these two intervals here. Then partial transpose density matrix can be given in this specific way, where we can see the color coding here that EJ and EL in the left-hand side has been interchanged their position in the right-hand side. In this same context, Perez-Ceredo-PPT criteria is another important criteria, which says that a necessary condition for separability of state is that the eigenvalue should remain positive if we perform this partial transpose operation over one of the subsystem. Here, rho A2 means that we are performing the partial transpose operation on the second interval A2. Now, if I say according to this Perez-Ceredo-PPT criteria, we can say that negativity is also a measure of the extent to which the eigenvalues are negative if we perform the partial transpose operation. In a mathematical way, we can write in this specific manner. Another point is that entanglement negativity provides the upper bound on distributable entanglement, which is basically the amount of quantum entanglement that can be extracted from a mixed state if we only use LOCC. In the context of mixed state, reflected entropy is another measure of that. Now, Pratik gave a nice talk on this same topic. So here, what we can say that A and B are two intervals here, or two subsystems here, which consists which consists a system which is a mixed state, and we try to purify it canonically by taking A star and B star, which are basically the copy of A and B. In that case, where we have A, B, A star, and B star, we can define a pure state root over rho AB, such that we can get back rho AB if we trace out A star B star from this density matrix here. When we have A, B, A star, B star, we can say that SR is defined as the von Neumann entropy of A star or the von Neumann entropy of B star. Now, if we start from the very beginning that A and B in a pure state, in that case, we can say that reflected entropy is going to be twice of SA, or it's going to be twice of SB. The holographic Renyi entropy is related to codimension 2 cosmic ray, which is homologous to the subsystem A. A is the subsystem which is sitting at the boundary, and now this cosmic ray has a tension which is proportional to n minus 1 by n. Now here we see that if we take n going to 1 limit, we can say that the tension is going to vanish, and in that case we will recover the RT. Now going to the next topic, which is the holographic reflected entropy. It has a nice dual which is called entanglement wedge cross section. It can be defined as the co-dimension 2 surface with minimized area dividing the total wedge of A and B. Now to understand that, we can look in this figure here, where A and B are two subsystems here, and we have a connected wedge. So now we can also have a disconnected wedge where A and B can be sitting far away. In that case, the situation will be quite different. But here we just take the connected wedge sector, where this blue area is the wedge of A union B, and we try to find the cross section of this blue area, which is the dotted surface here, and we try to again minimize it, and finally we get the entanglement wedge cross section. Now to explain the holographic reflected entropy, we have to take another copy of that, and we take that because we want to accommodate A star and B star as we explained before. And then we just cut out this red area and try to glue these two wedge region along this RT. And what we get is the right hand side scenario. Now here we have A star and B star, and the wedges are glued along this RT here. In this scenario, we try to find out the one Newman entropy of A star or B star. In both the cases, what we get is this blue circle here. And so it is nothing but twice of the area of EWCS. So we can say that SR is twice the area of EWCS here. Now holographic entanglement negativity has also a nice interpretation here, but it has basically two different proposals. First proposal was proposed in these two papers, where holographic entanglement negativity was proposed as an algebraic sum of linear entropies of order half. Now we take a disjoint interval A and B here, and C is an interval which is sandwiched in between A and B. And in that case, if we consider it as DCFT2, negativity can be expressed in this precise manner, where we see that these terms S half A union C, these are like linear entropy of order half. Now we have to take different kind of combination here, A union C or B union C, A union B union C, or C alone, and we can formulate the negativity here. Now when we have the answer for disjoint interval, we can also take C to be very, very small. In that case, what we will get is the adjacent interval result. By taking that, we're going to come here, and also we can write that negativity is half of this, the mutual information of order half. So that is another outcome of this result. Now again, the single interval case is quite tricky, where we have to consider B1 and B2 two auxiliary intervals on both sides of A, and then we take bipartite limit, where we take B1 in and B2 is full AC or A complement. In that bipartite limit, the negativity can be written in this specific manner here. Now all the results coming from these proposals match exactly with the CFT2 result if we consider the central charge to be very large. There is another proposal which says that entanglement negativity is related to the reflected entropy of order half. It was proposed in these two papers. In the first paper, negativity was proposed to be the dual to back-reacted EWCS, and also in that same paper, a quantum corrected version was developed, which can be written in this specific manner. Now in the later paper, a concise version was also proposed, where negativity was written as half of reflected entropy of order half. Now further in this paper, the sum of the result of this paper was further defined, and that was the outcome of this paper, the third one. Now before going to the island proposal for entanglement negativity, first I will try to go through the island for entanglement entropy. The key point of this is that fine-grained entropy of a region in QFT, which is coupled to a semi-classical gravity, is given by the island formula, which is written in this specific way. Now this ISA is the island corresponding to the subsystem A, and this term is the effective von Neumann entropy of quantum matter fields present in A union island of A. Now, from pictorial point of view, we can say that this is in the Bath region, or this is the region where only KFT lies, or if we consider only ADS3 CFT or that dimension, we can say that CFT2 is living on this Bath, and we have this JT brane, which gives us the semi-classical gravity here. Also, the CFT2 is extended in this region as well. Now, if we try to find out the entanglement entropy of the region A, we have to consider another region which is buried inside this JT brane, which is ISA, or the island of A. Now, having these two regions, we can now write this island formula, where the first term is giving us the area of the endpoint of islands, and second term is usually giving us the effective Bondiman entropy. In the same way, we can write the island for reflected entropy, where it was proposed in these two papers. It was written that SR has a sum of two different terms. First term is twice the area of a special surface, which is Q prime. Now, Q prime is the intersection of the boundary of reflected island A and reflected island B. And the second term was the effective reflected entropy of bulk quantum matter fields between these two regions. Now, this Q prime is a special surface here, which is denoted here in this picture in this black dot. We have considered A and B to be two subsystems here in the Bath, and then we try to configure the reflected island A and reflected island B here. So we can say that in general, reflected island and entanglement entropy islands are not exactly same, but yes, we can say that when we have the entanglement entropy island for A union B, which is this region here, the full region here, we can chop it into two parts. One part we can name it as reflected island A, and another part is reflected island B. This is what is happening here. So we are having the contribution of the first term from this black dot, and the second term is basically the effective reflected entropy. In the same way, we are going to propose an island for entanglement negativity. Now, if we go through the first proposal, then we try to define the any generalized island formula for entanglement entropy in this way, where we see that the formula has been raised to an index n. Now, if we follow the first proposal, which says that negativity is related to a special sum of any reflected entropy of order half, we can now express the island formula for negativity as a combination of generalized any entropy of order half. Now, here we consider the two disjoint interval A and B. Of course, C is there, but C is sandwiched in between A and B. And in that scenario, we can write generalized negativity as the half of the special combination of generalized any entropy of order half. Now, when we have this, we can take this answer and we try to extremize over Q double prime surface. And if we get more than one suit, then we will take the minimum answer, and that will be my island corrected formula for negativity. Now, what is this Q double prime surface? Q double prime surface is the intersection of the boundary of negativity island A and negativity island B. Here also, when we have the island for total A union B, entropy island of A union B, we can again chop it into two parts, where we can name one as negativity island A and name another with negativity island B. And in general, we can say that these negativity islands and entropy islands are not exactly the same. Now, having the disjoint case result, we can take C to be very, very small, and we can come to this result where we can have the generalized negativity for two disjoint intervals. Now, for single interval as well, we can again take B1 and B2 to be two auxiliary interval on either side of A, and finally taking this precise bipartite limit, we can have this answer. Now, in all the cases, we have to take the sum and then perform the extremization and minimization over the parameter Q double prime. Now, here we say that whenever we take the sum, all the parameters except Q double prime gets cancelled out. So whatever is remaining, that is only Q double prime here. So we have to extremize and minimize over the single parameter, which is Q double prime. Now, we can also come to the island for negativity using the second proposal, where we have to first define the any generalized reflected entropy. It can be written in the specific manner, where we see that n and m are two indices now. Now we take m going to 1 and n going to half limit to get the generalized any reflected entropy of order half. Now, when we have that, we can write generalized negativity as half of generalized reflected entropy of order half. Now, when we have these two proposals in hand, we can write a generalized island formula for negativity, which can be look like this one here, where we have a generalized negativity as the sum of two parts. The first term is a back-reacted area of Q double prime surface, and the second part is the effective negativity of bulk quantum matter fields between these two regions. Now, this Q double prime surface is the same as I explained before. It is the intersection of the boundary of corresponding negativity island A and negativity island B. Now, I will try to sketch some of the double holographic scenario for this proposal. First, I will try to explain some double holography for entanglement entropy, which is proposed in this paper. But yes, we can have many more names here as well. So, key point of this proposal is that the island formula for entanglement entropy can be written as the sum of two area terms here. Now, the first area term is the same as we have seen in the island formula. But what about the second area term? For that, we have to consider the CFT2, which is lying on this whole region, to be holographic. In that case, we can expect a bulk dual, which is lying here. And if we can consider that, then we can write the second term, which was the effective entropy term of interval A union island of A. We can write that in terms of area, which is this one, this blue line. So we can see that the island formula for entanglement entropy can be written as the sum of this blue line, the area of this line, and also this special green dot sitting here. Now, in the same way, we can explain a double holography for reflected entropy as it was proposed in these two papers. It is the sum of, again, the two area terms here. The first area term is this special green dot, which is sitting at the intersection of the reflected island A, reflected island B, and also the second area term, which is basically giving us the entanglement wedge cross section in this region. In the same way, we can understand our negativity proposals. For that, we try to consider the double holography expression for generalized any entropy of order half. Now, here we say that entangling surface has the spherical symmetry. Now, when we have the spherical symmetry, we can write the special form where we can write S gen of order half as a proportionality constant times the S generalized entanglement entropy of order 1. Now, in that case, we say that this is the proportionality constant which depends on the dimension and also the geometry of the surface. Now, when we have the expression for generalized Rayleigh entropy of order half, we can again take the combination and we can propose negativity in this form. Now, also according to the second proposal, we can propose double holographic scenario for entanglement negativity, but the SR half, the S generalized half, can be replaced as chi d times SR. If we do that, we will get this precise formula here, and we can write negativity as the curly line. But now we have the liberty to take it here, the back reaction effect here, and we can write that this is the dashed line and the green line, a green dot here, which is the second this term in the bracket, and we just multiply with chi d terms, and we get the answer. Now I will try to show some of our result. We have considered a specific model which was explained in this paper, where a zero temperature black hole was considered in 2D JT gravity with the matter given by CFT2. And we then couple it to a bath living in the half Minkowski space, which has the same CFT2. And then finally, we impose transparent boundary condition for the easy flow of modes. And in that case, if we take a single interval 0 to B in the bath, we can write the generalized entropy in this manner. where phi is the corresponding dilaton fields, and phi naught denotes a constant which contributes to the topological entropy. Now here we consider an interval C1, C2 in the bath, and also we have corresponding island AC1 and AC2. In that case, we try to write generalized Rayleigh entropy of order half, which can be written in this specific manner, where we see that we have multiplied this chi2 terms, which is 3 by 2. We have taken chi2 because we are considering ATS3 CFT2 scenario, and these 3 by 2 terms are only multiplied in the second and third terms, not the first one, because the second and third terms are only the dynamical term here. So they are only going to get the back reaction effect. Now, when we have set the model, we can now consider two disjoint interval. One is from B1 to B2, this one, which can be named as A, and B3 to B4, which is this one, which can also be named as B. And then we try to compute negativity from both the proposals. And what we get is the answer, this one, written here. So both the proposals are giving the same answer. Now, we can change the size of the subsistence here. We can change the subsistence size A, B, or both, and we can have many more phases. Now just take a situation where A and B are small. In that case, if this is the subsystem we consider C, then C is very large. In that case, A, B both has the disconnected wedge. In that case, when we have the disconnected wedge, intermittent wedge cross section is identically 0. So negativity is also 0. And if we just invoke the same condition in the first scenario, we can also get the negativity to be 0. Another condition is that we can have A to be very, very small. In that case, what we have is this EWCS line is going to land here in this black RT. So we can calculate negativity for this kind of situation as well. And also, if we try to invoke the same condition in this scenario, and we try to compute entanglement negativity via the first proposal, we are going to get the same result as the second proposal. So we can say that all the results are matching for all the phases. And we can then go to the adjacent interval case and as well as the single interval case. And there also we see that the exact matching of result from both the sides. Further, we consider another model where an eternal black hole has been considered in 2D JT gravity with matter given by CFT2. Now we couple two rigid half-Minkowski space on either side of the gravity region with the same CFT2, and then we impose transparent boundary condition at the interface. In that scenario, as earlier, we take another interval C1, C2 on one side of the bar. Now it has an island AC1 and AC2. In that case, we again write generalized Rayleigh entropy of order half in the specific form. Here also we see that the proportionality constant chi2, which is 3 by 2 again, is multiplied in the second and third term only, not the first term. Now in this situation, we can consider two disjoint interval. Now here it is A and B. One is in the left side and there is the right side. And we can have C, which is a very small. We can say that it is some interval which is sandwiched in between A and B. And in that case, we try to use both of the proposals to compute negativity. And what we get from both the proposals is this answer. Now, one crucial point is that here we have to take C to be very, very small. Otherwise, the wedge of A and B will be disconnected one. In that case, we will get 0 negativity. So we can consider different type of phases, and also we can consider negativity for adjacent and single interval case. And what we saw that the result using both the proposal match exactly for all the cases. Now, as I have time, I will go to the replica one more scenario where we see, where we first understand, try to understand this construction in this paper, where negativity was proposed as even analytic continuation of Rayleigh index 2n. Now this 2n replicated boundary manifold is M2n AB. where A, B denotes the fact that A and B group cyclically and anticyclically respectively. Now this Z2n symmetry on the boundary doesn't always extend to the bulk saddle points. Now we will get the most interesting result when this Z2n symmetry doesn't extend to the bulk saddle points. But when it does, what we get is identically zero result for negativity. Now, this one is called replica non-symmetric saddle. We have to take to a number of copies, and on each copies of bulk manifold, we consider a cut along 3 non-overlapping codimension 1 homology hypersurface. This is sigma A, sigma B, and sigma AB bar with this specific condition. Now, this gamma X denotes a codimension 2 hypersurface here. Now, when we have this scenario, we try to glue along this sigma A surface the odd number of copies of bulk manifold cyclically and even copies to themselves. We can see it from this figure. These odd copies 1, 3, 5 you can do cyclically for A and B with themselves. Now the same way for sigma B, we try to glue the even number of copies of bulk manifold anticyclically and odd copies to themselves. And for sigma AB bar,
Jaydeep, you have about 5 minutes.
Okay,
you have about 5 minutes left.
Okay, thanks. And for sigma AB bar, all the copies we glue pairwise, starting with the first one, finishing with the last two. Now, if we glue in this specific manner, the replica symmetry group Z2n breaks into a subgroup Zn. Now, taking the Zn quotient manifold, we can have the asymptotic boundary M2a, B, which is in case the same as M2ab, because when we have two copies, you can't differentiate between cyclically and anticyclically. Now, the quotient manifold has a conical defect at gamma A1 and gamma B2. And we have the backreacting cosmic branes, which is homologous to the subsystem A and B with this specific deficit angle. And then we go ahead, we can go ahead with the calculation, and we get the negativity as a half of mutual information of order half. Now, if we just try to accommodate island for this replica non-symmetric saddle, we consider a quantum field theory coupled to gravity on a hybrid manifold M, where M fixed is non-gravitating and M bulk contains dynamical gravity. Now, this quantum field theory is extended throughout the M, but gravity is bounded in M bulk only. Now, we use the same procedure as explained before, and what we get is this specific answer, where generalized negativity can be written as half of generalized mutual information of order half. Now, if we consider two adjacent interval results, the above result match exactly. But what about the disjoint case result? So in that case, we take A and B, two separated interval, which is disjoint interval, and C is there as well as it's another disjoint interval, which is sandwiched in between A and B. It makes the full system A union B union C compact and also makes it a pure state. In that case, if we try to compute generalized negativity, we can have this specific formula. Also, for a single interval A with two auxiliary interval B1 and B2, we can have the generalized negativity as the specific manner when we consider this bipartite limit. Now, these three are the formula which we have used in the first proposal. So we can say that the first proposal has a proof in this manner using the replica wormhole scenario. Now I will try to summarize my talk that we propose two alternative construction for island contribution to the entanglement negativity. The first proposal involves specific algebraic sum of generalized any entropy of order half. The second proposal involved generalized any entropy of order half, and we applied our island proposal to compute negativity for various cases, and what we saw that the results match exactly for all the configurations. We also tried to sketch a possible double holographic scenario for our island proposal, and also in the end we obtained a proof of our result using replica wormhole technique. So in this context, I would like to say that the matching of this result, one from the algebraic sum, another from the generalized any reflected entropy order half, the matches only up to a constant. Recently, there has been a paper where we see that this match is only up to a constant, but the functional form match exactly. Okay, so that's what I have to say. Thank you.
Okay, let us thank Jaydeep for a nice talk. If there are any questions, comments, you may please raise your hand. There are any questions, comments? Okay, if there are no questions or comments, let's thank Jaydeep again for a nice talk. And I'd like to see if Akrajyoti is already here.
Yes, yes.
Jaydeep, you may stop your screen. Yeah.
Hi, Jaydeep. I have one question, very basic question.
Yeah. Please go ahead.
Yeah. Yes.
Why do we need entanglement negativity? I mean, this is one-moment entropy is not enough for some reason.
Yes. So for the mixed state, we need entanglement negativity, because in mixed state, what entanglement entropy gives us is not exactly the entanglement what we need. As example, I can tell you that for finite temperature CFT, if we consider single interval there, and you try to compute entanglement entropy, what you will get is the entanglement entropy and also the thermal contribution there. So that's what we don't need. We need only the entanglement we only need the quantum entanglement from a mixed state. In that case, you have to consider entanglement negativity. That's the way out.
Okay, thank you.
Yeah, thanks.
Hello. Hello.
Yeah, Akrajyoti.
Yeah.
Kindly share your screen and
Yes,
go to
yes.
full screen mode. Yeah, that's your screen. Yeah.
Okay. Let me first thank the organizers for giving me this opportunity. The title of my talk is Scattering Amplitudes from Generalized Recursion, which is based on these two works. These works are done in collaboration with 𝗰𝗵𝗶𝗶, who is a postdoc at 𝗰𝗵𝗶𝗶. Okay, so let me begin with the motivation for the on-cell recursion method. The basic idea of recursion relation is to obtain higher point amplitudes in terms of lower point amplitudes. For massless particle amplitudes, the BCFW relations is one of the most powerful tools in which a pair of massless external momenta gets complexified. In the spinor helicity formalism, the BCFW recursion method makes the computation of complicated amplitudes simple by requiring only 3-point on-cell amplitudes. This is advantageous over the usual Feynman diagram techniques, which is not recursive, and unit-IT method, which requires manifestly off-cell 3-point amplitudes. Although the spinor helicity formalism for massive particles has been known for decades, but those variables are not the most convenient for computation of S matrix, as they were not little group covariant. Because why we need this covariance? Because the S matrix itself are covariant under the little group. So it is desirable to work with variables which are themselves covariant under the little group transformations. So it was the work of Arkani Huang and Huang in 2017 who introduced little group covariant spinor helicity formalism for massive particles. In certain sense, their formalism unifies the kinematic space of massive and massless particle into spinor helicity basis. Also, this formalism allows one to take the massless limit of a massive amplitude in a systematic manner. So what do you want to do with it? So in light of this discovery, it is natural to ask how democratic is the on-cell recursion of complexifying arbitrary external momenta. That is it possible to complexify massive external states leading to a consistent recursal relation while keeping the latent group covariance intact? In our first paper, we introduced a shift which involves one massive and one massless spinor helicity variables. An important result of this work is that we classify all such allowed for the Higgs-Triangle theory that I will describe. In a follow-up work, we used these shifts to compute two classes of amplitudes involving massive vector boson in the Higgs-Triangle theory. These amplitudes are the massive analog of MHV and NMHV amplitude. Okay, so let me briefly review what is the spinor helicity formalism. For massless particle, the momentum for vector written in this SL2C representation becomes a 2x2 matrix, and because of the on-cell condition, the determinant is 0, which makes this 2x2 matrix rank 1, which implies that this matrix can be written as a product of two component two spinor variables. So basically, they are coil type of spinors. So we call these spinors as massless spinor helicity variables, and in light of this relation, the little group scaling for massless particles looks like this. It's just a scaling where T is some non-zero complex number. So the massless amplitude often written in terms of some spinor object, which is either written either the product of this lambda variable or lambda tilde variable. The angle brackets denotes the contraction of two lambda variables, and the square brackets denotes the contraction of two lambda tilde variable. So under this little group transformation, the amplitude, massless amplitude, scales like this, right? Where I have considered one massless particle with helicity H, and I am considering little group scaling of the spinor helicity variables associated to that massless particle. So it scales like T to the power minus 2H. Okay. Now let me tell you about the spinor helicity formalism for the massive particles. So for massive particles, we just express the momentum matrix as a sum of two component product of two component spinor helicity variables. So there is an extra index I here, which will turn out to be the SU2 little group index for the massive particles. And the little group transformation for these variables looks like this, where this W is in the SU2 matrices. Similarly, for massive amplitudes, we will define some Lorentz invariant objects, but these objects are covariant under little group because they manifestly carry these IJ indices. Okay. So now let me go to the what is called generalized recursion. To do this, let us so the amplitude. The amplitude is a function of external momenta, and we pick any two momenta, which one of them are massive and one of them are massless. So we pick two momenta and complexify them in this fashion. So here we did this deformation while keeping all the momenta on cell always, and the plus minus comes from the fact that we want to keep the overall momentum conservation intact. So on-cell condition imposes further these following relations. With this complexifying, one can extract the physical amplitude from the complex deformed amplitude from a simple contour argument, and it takes the following form. So the important point is that the physical amplitude is now a product of on-cell on-cell lower point amplitude AL and AR. Here I have two terms, basically because of the fact that there may be both massive and massless channel present in the scattering diagrams. So in writing this factorized form, we have assumed that so diagrammatically, factorization means is that we have a endpoint amplitude, and this factorization looks like this, where the two deformed legs are attached to two different sub-amplitudes. Okay, so with this factorization, this Onsel recursion method works for amplitude that are forced to exist by consistent factorization given the three-particle amplitude. So this excludes theories with contact terms because the contact terms cannot be factorized in this fashion. So one of the example is the famous 𝗬𝗲𝘀 theory. So the momentum shift introduced here can be realized in terms of the massive spinor helicity variable in this fashion. Where one important remark is that these deformations are now covariant under the little group as the massive spinor helicity variable carries explicit SU2 index. Okay, so we denote such shift where this as IJ plus. So we have picked one of the massless particle to be J, and suppose and the helicity of that particle is mentioned like this, plus helicity, and the bold-faced I means the ith particle is massive, and we are deforming the lambda tilde variable in such fashion. So so this is one of the example of massive massless shift of the type M plus. So similarly, there are three other classes of massive massless shift, which is like this. Okay. So okay, let me briefly talk about the larger behavior of the amplitude. So one of the key ingredient for the Onsel recursion to work is that the amplitude must decay at large jet. But this assumption is far from obvious and not even true for any general theory. Naively, individual Feynman diagrams behave like this, where each vertices, for gauge theory, each vertices will scales with Z, and for gravity, it will be Z square. And all the propagators in between them will scales like 1 over Z. So individual Feynman diagram always diverge for both gauge theory and gravity. But surprisingly, at least for some helicity configuration of the deformed external particles, the amplitude does vanish at large jet. BCFW explicitly shows for gauge theory shows that the helicity configuration of the deformed particles for these helicity configurations, the amplitude behaves as 1 over Z at large jet, but the helicity configuration for plus minus, it scales at Z3. So in our earlier work, we show that the generalized recursion is consistent for Higgs-Yang-Mills theory, for which amplitude does decay at large jet. And as a consequence, we also showed that there are out of 4 types of massive masses, possible massive masses shift, only these 2 types of shifts lead to consistent generalized recursion. So is there any question at this point? Okay, so now let me move on. So what is this new recursion is good for? So the natural question is that how powerful and efficient this massive massless shift over 2 other possible 2-line shifts, namely both massless or both massive deformations. And another question is that is it possible to compute certain class of amplitude in a more optimal way using this generalized recursion relation than the famous BCFW recursion? So we probe into these 2 questions by studying 2 classes of tree-level color-ordered n-particle amplitude by using generalized recursion. So, the first class is that we consider 2 massive vector bosons and arbitrary number of identical gluons. So this massive amplitude is the closest analog of MHV amplitude. And the second class is that we consider a pair of massive vector boson, one minus helicity gluon adjacent to one of the massive vector boson, and all the rest of the gluons are positive helicity. So this massive amplitude is the analog of what we call NMHV amplitude for in the case of pure gluon amplitudes. Okay, so let me first describe the amplitude with all identical ones. So we consider the shift on particle 1 and 2 like this, and all the possible channels for this scattering amplitude are shown in here. There are 4 diagrams. The first and third diagram vanishes because single massive vector boson, like here and here, massive vector boson cannot decay into identical gluons. And the second diagram vanishes as a pure gluon amplitude, either have one single negative helicity or all positive helicity gluon attached to it. So both of them are 0. So only this last diagram remains. So we find the amplitude using the principle of induction and generalized recursion to be like this, but this one n is a spinor product involving the massive spinor helicity variables of the particle 1 and 2, which is defined to be like this. So it is defined as spinor product, a symmetric product of the this angle. So to see whether this amplitude produce MHV amplitude in the massless limit, we take the following. We consider the following. So as a general rule of thumb, the massive spinor behaves in the massless limit as follows. The angle massive spinor in this massless limit goes to massless particle with helicity negative helicity particle, and for the square bracket, for the square variable, it corresponds to plus helicity massless particle in the massless limit. So with this, you can see that only angle bracket involving 2 massive spinor helicity variables are appearing. So in the limit, there is only one non-vanishing configuration, which is exactly produce the MHV.
Akrajyoti, you have 2 minutes left.
Okay. So the other possible amplitude is gluon with a flipped helicity gluon. So we consider this 1-2 shift again. As we consider only minimal coupling, the Xn particle can be either massive vector boson or gluon. But a massive vector boson cannot be possible because it cannot decay into 2 massless gluon, as we see. So earlier, due to 2-1 shift, the first diagram get non-zero configuration only for this helicity configuration. Okay. So again, we use generalized recursion, and the amplitude can be computed from scratch. The answer is look like something like this. And if you take the massless limit, there will be 3 possible massless components in this limit. So one of them, so here 1 and nth particle are massive. So we take minus plus combination first. It will and plus minus combination. So for both opposite helicity configuration in the massless limit, they reduce to MHV type of amplitude. But if you take negative helicity configuration for the massive particle in the massless limit, it will produce the NMHV amplitude. So I just want to mention that why the generalized recursion is advantageous over the BCFW. So if you see this flipped helicity configuration, if you use BCFW type shift, like I did on 2-3, there will be 2 possible channels. But this second diagram, in this context, always involve the amplitude with configuration which we intended to compute, like this sub amplitude involves a gluon with negative helicity itself, and all the other particles are positive helicity. But this is the exact configuration that we are trying to compute. But in the case of generalized recursion, what happens that all the sub amplitude involved in this scattering channels are already known. So it is the sub amplitude are either of the type 2 massive vector boson with all plus helicity gluon or the pure gluon amplitude. So in using generalized recursion relation, one can compute this amplitude from scratch. But if you use the BCFW, you need some extra data. I mean, there's some assumption. Then you can do inductively prove that assumption if you do that BCFW. Okay, I just take one more minute. So although we have considered a specific holistic configuration for external gluons, it is possible to compute scattering amplitude involving gluons with arbitrary helicity using generalized or BCFW shift in combination with the amplitude we have considered here. However, in order to compute amplitude with more than 2 massive particles using generalized recursion, one would require knowledge of a wider class of amplitude. So we haven't done this, but we hope to address this problem in the near future. And another obvious step would be, it would be interesting to explore the usage of this new recursion in computing various loop amplitudes. Thank you.
Okay, thank you very much, Akrajyoti, for your nice presentation. So I would like to see if there are questions, comments on this. If you want to ask a question, you can please raise your hand or something so that we can see. Okay, that is all right. Okay, if there are no questions, comments, let us thank Akrajyoti again. Sukrut Mondkar,
yeah,
can I see you or see your screen? Can you share your screen? Yeah. Share your face or something? Yeah, I can see you and your screen also. No, this is not yours. Yeah, go to your first page.
Oh, sorry, the last.
Yeah. That's okay.
You can see the hand tool also, right? The hand.
Yes. Yeah. So let us welcome Sukrut Mondkar from IIT Roorkee. So he will be talking about
IIT Madras.
Sorry, IIT Madras, yeah. IIT Madras. So he will be talking about relaxation dynamics of a semi-holographic flat brane and open quantum systems. So I will knock you at 13 minutes.
Okay.
You can try to wind up there. Okay, thanks. Please go ahead.
Yeah, so thank you for the opportunity to speak in this conference. Now, the title is this: Relaxation Dynamics of Semi-Holographic Backplane and its Connection to Open Quantum Systems. And it is based on this paper. Yeah, so this is the this figure is a schematic of heavy ion collision experiments where two heavy nuclei traveling at ultra-relativistic speed collide with each other, and that produces a deconfined state of quarks and gluons at very high temperatures and densities. So then this matter produce goes through various stages of evolution. So at early stages, when energies are very high, the weak coupling description such as kinetic theory is suitable, whereas in the quark-gluon plasma phase, which is produced at intermediate stages, can be described is a strongly coupled fluid with very low value of viscosity to entropy ratio. So this is so basically at different stages, this matter admits different effective theories as best physical description. So these are the plots for such different poles of retarded propagator or singularities of retarded propagator in different such effective theories. So all of these effective theories are same hydrodynamic pole, which is this cross, blue cross, whereas the non-hydrodynamic singularities are different in different effective theories. For example, ADS-CFT has this Christmas tree polynomial modes arranged in Christmas tree structure. The kinetic theory has a branch cut which correspond to localized quasi-particles. Israel's toward hydrodynamics has one non-hydrodynamic pole on negative imaginary axis and so on. Even though these theories describe different aspects of heavy ion collisions, the QGP, quark-gluon plasma itself, can have very different non-analytic structure. So we would like to see what happens, like how this non-hydrodynamic modes change when we couple a weak description like a kinetic theory with some strong description, like some strongly coupled holographic theory. So as the first step, we couple instead of kinetic theory, we just couple a massless scalar field with a strongly coupled holographic theory. So that is the model that I will describe now, which is in the paper. So in this model, this is the action of the system S. So first term, so chi is the massless scalar field. So first term is the action for massless scalar field, and then the other thing is this strongly coupled holographic CFT. So WCFT is the action for this strongly coupled CFT. Small h is the source which deforms this CFT. Now the two sectors talk with each other via this special kind of coupling called semi-holographic coupling, where the source of each sector is promoted to be the functional of operator of other sector. So the source that deforms the strongly coupled sector, the CFT, is operator of this weakly coupled sector, this massless scalar chi, and this beta is the called semi-holographic coupling. Now this massless scalar can be thought of as some composite gauge degree of freedom, like a meson or baryon field. And it can be a goldstone of some spontaneously broken symmetry. Now, since this coupling is linear, therefore it will modify the. So since CFT is holographic, it is dual to some black brane in the bulk with the deformation corresponding to the dilaton in the bulk. And since this coupling is linear, it will modify the Quasinow mode spectrum of this black brane, which is dual to the CFT. Now this 𝗦𝗀𝘀𝗀𝗃 is the CFT operator dual to the bulk dilaton. And according to ADS-CFT dictionary, we have this relation where WCFT is same as the on-shell gravity action of dual gravity theory, with the source small h replaced by this 𝝅0, which is the leading term in dilaton near boundary expansion. So we have, these are the equations of the system. So firstly, holographic sector has this Einstein equations and Klein-Gordon equation for bulk dilaton. Then as I said earlier, there's the two sector talk with each other by sourcing each other. So the massless scalar of the scalar sector sources this holographic sector by this semi-holographic relation, 𝝅0 minus beta chi, and a CFT operator chi sources the scalar sector, boundary scalar sector, by modifying its equation like this. So each sector is sourced by the other sector. Since both boundary scalar chi and this bulk dilaton phi are massless, the model has these two shift symmetries, but these two shift symmetries are not independent, but they are broken to diagonal because of this semi-holographic coupling, this relation. So the full system stress tensor is the sum of the stress tensors of individual subsystem, and the subsystem ward entities imply that this full system energy momentum tensor is always conserved. So I will describe now the results of the paper. So firstly, we compute the Quasinow modes of the hybrid fluctuations of this bulk dilaton and the boundary scalar chi about the equilibrium background. So the equilibrium configuration is ADS4 Schwarzschild black brane with vanishing phi and vanishing chi. So these hybrid Quasinow modes should satisfy these two boundary conditions, which are generalizations of the usual Quasinow mode boundary conditions at boundary and horizon. So first is equation of motion for the boundary scalar by using this semi-holographic relation, and second is the expression for the CFT operator H obtained from holographic renormalization. So I will show the results for the homogeneous case when k equal to momentum is 0 with this animation. So so in this animation, the beta is increased from 0 to larger values. So for first snapshot is when beta is 0. So we have these decoupled Quasinow modes of the strongly coupled sector and these two 0 modes sitting at the origin. Now I'll play the animation. So one of the 0 mode is lifted because of the semi-holographic coupling and moves down the negative imaginary axis. Whereas there is another mode, two more modes that appear, one moving up from negative imaginary axis and one on the positive imaginary axis. Now this one moving from negative imaginary axis collides with this lifted zero mode. We call it a quasi-hydro mode. And the two become propagating mode after collision. Whereas there's one on the positive imaginary axis, it just stays there, but moves closer to the origin. So firstly, at large values of beta, with this dimensionless combination, the positions of these modes becomes independent of each other on this complex frequency plane, independent of beta on the complex frequency plane. So temperature is the only scale that remains in the problem. So there is an emergent conformality in the hybrid system at large values of beta. Secondly, that even though there is a pole on upper half plane, the system is stable. There is no instability since the total energy is the sum of the energies of the individual sectors, the scalar, boundary scalar, and the holographic sector. And each of these energies is positive definite and bounded by above by the total energy. So there is no instability. Now, as I will show in the with the result of nonlinear simulation, that this unstable mode drives the initial transfer of energy from black brane to the boundary sector, whereas this quasi-hydro mode, which is this lifted zero mode, drives in all the energy in the system to the black brane at asymptotically late times. So this quasi-hydro mode is parametrically close to the origin, have small values of the coupling beta, and therefore this late time transfer is very slow to the black brane. Yeah, so next, so far I only talked everything was only at linear level. So now I will describe the results of the nonlinear simulation. So we start with some nonlinear, start with the initial state of this hybrid system and study its time evolution. So I will skip the details of the calculation, only show the results. So the top plot is for the boundary scalar, time evolution of boundary scalar, chi. So the black dashed line is when beta is 0, when it is decoupled from the holographic sector, it will be just a straight line. But when it is coupled, so for beta equal to 0.1, the blue curve, so it will eventually at asymptotically late time, it will become flat. So the chi will become constant. So lower two plots are for the energies of the E subsector. So the energy of the boundary sector E kinetic, which will be half chi dot square. So at late time, since chi becomes constant, it will go to 0. And yeah, so as anticipated, and all the energy will be go to the black brane at late times. As anticipated from the positional mode analysis, at early time, some of the energy from black brane is absorbed by this boundary sector, and this is driven by that unstable mode that I showed you. Whether late time, all the energy goes to the black brane, and this late time transfer is driven by this quasi-hydro mode, which is parametrically close to origin. Yeah. So this model is naturally a model for open quantum systems because, so think of this chi as an open system, and this black plane or the holographic system as the bath. So the dynamics will be non-Markovian because there is always because the correlation between the black brane and the boundary sector decays only at asymptotically late times when system thermalized. Till then, since the modes are hybrid modes, the two sectors are always correlated at all finite times. And also the total energy, also the energy of, since total energy is finite, the energy of the bath is always finite and not infinite, as is usually the case for Markovian things. So now I will describe the final section, the quasi-normal modes in the presence of inhomogeneities. So firstly, there is also an emergent conformality, just like for k equal to 0 that I showed earlier at large beta. Now there is a diffusive mode at small k, and as one increases the value of k, then this diffusive mode collides with the quasi-hydro mode that I showed earlier, and both become propagating mode. And both the modes are the branches of the same dispersion relation called as k-gap dispersion relation, which is found ubiquitously in many different areas of physics. Then there exists a zero mode at non-zero k in this model, and it gives rise to instability, which is reminiscent of Gregory-Leflamp instability of the black strings in higher dimension. So I will describe all these points with just this one animation. So this is animation for beta equal to 0.35, and in animation k is increased from 0 to larger values. So this mode is the quasi-hydro mode. This is this unstable mode, and this is the another mode that comes from negative imaginary axis. I'll just play the animation. So now in animation, the mode that comes down from the origin is a diffusive mode. It will collide with this quasi-hydro mode, as I said, and both become propagating, and all are the branches of same dispersion. Both have branch of same dispersion relation called as K-gap dispersion relation. And this mode on the negative imaginary axis, it will move up and pass through the origin and then become unstable. So this is the reminiscent of the Gregory-Leflam instability. And since it passes through the origin, that means there is a zero mode at non-zero value of K. So this implies that the black brane solution is not necessarily the final state of the time evolution. There could be a turbulent behavior or glassy behavior, which one has to investigate. Yeah, so let me just conclude. So we study the semi-holographic coupling between the scalar field on the boundary and the black brane in the bulk. We see a lot of interesting results of the quasi-normal mode analysis and also the nonlinear simulations, such as emergent conformity and others that I explained. So this model is a model. This is a good model for an open quantum system where the bath has a finite energy. Then as a next step, we have already made some progress in coupling a kinetic theory on boundary with the massless scalar. And yeah, so an interesting question to ask is, once we quantize the boundary scalar, will it be able to maintain the long time coherence at small couplings, just like for this current case where the boundary scalar is not quantized? And one would like to investigate the fate of this Gregory-Leflam type instability by doing the full nonlinear simulation. Thank you.
Okay, thank you very much, Sukrut Mondkar. There are questions and comments. You may please.
I have a question. May I ask?
Yeah.
Yes, please.
Yeah. The question is, how do you make very sure that this is a very good model of open quantum system? Because in open quantum system, we do the analysis in a completely different language. I know that you have approached the problem from a little bit QGP side, but could you please tell us why you are so sure that this is a very good model of open quantum system? We usually talk about density matrix, its evolution and all. Okay, so I can't see that features of open quantum system. It's not about only bath. Like, could you please tell what you exactly want to mean?
Okay, we haven't investigated in this direction. This is just some analogy I was giving. But the idea is that one important thing is that there is always a memory between, because of this finite energy. There's always a correlation.
No, my question is, so since open quantum system you mentioned, there are two possibilities, like either this is Markovian or non-Markovian.
Yeah, this will be non-Markovian.
You are considering non-Markovian, okay.
Yeah, yeah. Okay. Because there is always a correlation, so there is a memory with the bar.
Okay.
And we can solve for the full dynamics.
Okay. But have you investigated those possibilities?
No, that we'll want to do, but we haven't still done that.
Okay. Thank you.
Okay, if there are other questions, comments. Okay, if there are no other questions or comments, let us thank Sukrut for the nice presentation. And you may stop sharing your screen. Can I see Debodirna Ghosh?
Yes, I'm here. Yes.
Yep. Please share your screen.
Yes. So can you see my screen? Hello. Am I audible? Can you see?
Yes, you can see. Yes.
You can see my screen?
Yes, Debodirna Ghosh.
Yes.
And he will be talking about super translations at time like infinities. So I will knock you at 13 minutes. Your talk is of 15 minutes. At 13 minutes, I will knock you so that it can end up in next one.
Okay.
Please go ahead.
Okay. So thank you. And I'd like to thank the organizers for giving me an opportunity to speak here at this edition of Indian strings meeting. The title of my talk is Super Translations at Time Like Infinity. This work is based on this paper that I've done in collaboration with 𝗰𝗵𝗶𝗶𝗍𝗍, Sumanta Chakravarty, Jahanur Haq, and Aniket Khairnar. This is the outline of my talk. So first I will give an introduction and then the motivation behind my work. And then I will talk about super translations at time like infinity and the associated charges to it. And if time permits, I will talk about the Schwarzschild solution at time like infinity, and then I will conclude. Okay. So the asymptotic properties of gravity have been studied extensively for decades in the context of understanding asymptotically flat spacetimes at null infinity. However, the symmetry group of asymptotically flat spacetimes are not the usual Poincaré group that we come across in special relativity, but the group is called a BMS group, and which is a semi-direct product of the super translation group and the Lorentz group. Under the BMS group, one asymptotically flat solution of general relativity at null infinity is mapped into another solution. The infinite dimensional super translation subgroup generate arbitrary angle dependent translations of retarded time. Now, the BMS symmetries are the exact symmetries of general relativity. One expects that the BMS symmetries to be present at a spatial and time like infinity, provided that the boundary conditions at a spatial and time like infinity are compatible with the boundary conditions at null infinity. Then a natural question to ask is, how do we relate the boundary conditions at null, spatial, and time like infinity? This is a very difficult question to answer. However, Hanno and Troissard in a series of papers have proposed boundary conditions at spatial infinity that are invariant under BMS symmetries. So our motivation in that aspect lies in exploring the boundary conditions at time like infinity for a nonlinear general relativity that realize the BMS symmetries in the sense that it has a non-trivial action on the asymptotic fields and have generically non-zero charges. Another motivation is that the recent studies by Hawking, Perry, Strominger, Curlip, and Donnet et al. Suggest that stationary black holes also possess an infinite number of symmetries in the near horizon region. It is believed that global charges associated with super translations receive contributions both from the horizon as well as from the null infinity. Thus, for a complete study of conservation laws associated with super translations, it is required to know the relation between symmetries at the horizon to that at null infinity. Time like infinity can be used as a link between the symmetries at the horizon and at null infinity. So in the next few slides, I will give a notion of asymptotic flatness. So introduce one notion of asymptotic flatness at time like infinity. It is based on the corresponding notion which was introduced by Bike and Smith at spatial infinity. To do that, we first introduce a set of polar coordinates tau, rho, theta, phi for Minkowski spacetime, where the coordinates tau and rho are given by these two equations. Here, eta mu nu is the flat metric where most of the diagonal signs are positive. In these coordinates, the flat spacetime metric takes the following form, where the line element ds square is equal to minus d tau square plus tau square times this line element. So this line element denotes a Euclidean ADS3 hyperboloid in the tau equals to constant hypersurface. So to understand what are the slicing, what are the tau equal to constant slicings, I draw this Penrose diagram of Minkowski space where scri plus and scri minus are the future and past null infinities, I plus and I minus at the time like infinities, and I0 is the spatial infinity. So here both the red and blue lines correspond to tau equals to constant slices. So we are only interested in these red slices because this on these red slices tau square is greater than 0, and these red slices correspond to this Euclidean ADS3 hyperboloid. Okay, so now as we move closer to the future time like infinity I plus, that is tau tends to infinity, we kind of zoom in the structure of the future time like infinity, which is denoted by this Euclidean ADS-C hyperboloid at the top of this diagram. Okay, so now that we know how, the future time like infinity, I mean the coordinates that we define rho, tau, theta, pi, the good coordinates to study the future time like infinity. So let us consider a general class of space-time, which is denoted here by this metric G mu nu is equal to eta mu nu plus the expansion over the negative powers of tau. Here, this tensor ln mu nu is a function, this tensor is a function of the Cartesian coordinates and the ratio of Cartesian coordinates and the tau coordinate. Then following Beigen-Smith, this metric can be put in the more convenient form where the line element ds squared is given by minus n squared d tau squared plus HAB d phi a d phi b. Here, a capital N is called a lapse function, which appropriately normalizes the normal to the slicing that we consider here. And the three-dimensional metric HAB is expanded in powers of 1 over tau, where the leading order term H0AB is our Euclidean ADS-C hyperboloid that I have just discussed. So this above Beigen-Smith form is our starting point. Now, in the next few slides, I will talk about super translations at time like infinity. So if super translations are the genuine symmetries of general relativity, then they should also be realizable at time like infinity. A natural question, therefore, to ask is, what is the set of diffeomorphisms preserving the form of the metric? So the following diffeomorphism preserves the asymptotic form of the metric 2 order 1 over tau. So where the tau bar and phi bar coordinates are transformed to tau and phi a. So here phi a collectively denotes rho, theta, and phi coordinates. So these are transformed by an arbitrary function on Euclidean ADS-C hyperboloid, which is omega, and this is a function of phi bar a, which are the rho, theta, phi coordinates. This arbitrary function determines the higher order terms in the diffeomorphism uniquely. We only focus on super translations in our work. Under general super translation, the 0th order field H0AB and the first order field sigma does not transform. The first order metric correction H1AB transforms under general super translations as the following, where the first order metric correction H1AB goes to H1AB plus twice dA dB omega minus twice omega H0AB, where this curl d dA is the covariant derivative compatible with the metric H0AB. Okay. Now, omega is an arbitrary function on the hyperboloid. It's a function of rho, theta, phi coordinates. So one needs to specify boundary conditions. The boundary conditions at such that the boundary conditions at time like infinity should remain invariant under the allowed super translations. To state the boundary conditions, we define a quantity KAB such that KAB is equal to H1AB, the first order metric correction, plus twice sigma, the first order field, times H0AB. So it follows that under general super translation, KAB transforms to KAB plus the quantity with which the H1AB transforms, as sigma and H0AB does not transform under super translation. Okay. So there are now two natural sets of boundary conditions that we can consider. First, one can dispose of super translations by demanding that KAB equals to 0. So if I go back one slide, here in this equation 2.5, so if we take KAB equals to 0, then dA dB omega minus twice omega H0AB equals to 0 has a solution omega which denotes translations. Another boundary condition we can take is the trace of KAB, which we call K, to be equal to 0. And we work with this kind of boundary condition where the trace of KAB equals to 0. It implies that the following differential equation of omega, which is box minus 3 omega equals to 0, will be satisfied. Also, we work with nonlinear gravity. Thus, we can obtain the second or higher order transformations of the fields. The action on the second order field is given by this second order metric correction H2AB transforms to H2AB plus the nonlinear terms, which are of the order of omega k, omega sigma, and quadratic in omegas. We find that the second order super translations are then consistent with the Einstein's equation of motion when the equations of motion are split into 3+1 form. Okay, so in the next few slides, I will talk about charges associated with super translation and Lorentz symmetries. Okay, so to talk about the higher world global charges, the contribution from time-like infinity, future time-like infinity to the higher world global charges, I draw this diagram, which is a diagram of a space-time without a horizon, where the boundary components are Scri plus and Scri minus. Now, to define the higher world global charges, one need to specify a Cauchy surface, Cauchy slice, sorry. So this Cauchy slice is given by this green line. And the first variation to the higher world global charges remains invariant under the local deformations of this Cauchy surface. So one can deform this Cauchy surface to far future or to far past. So for our case, we deform it to far future to I plus union Scri plus. Okay, so we would like to understand the contributions to the higher world global charges from time like infinity. The global charge variation remains invariant under the local deformations of the Cauchy surface sigma. So one can deform sigma in the far future to I plus union Scri plus. In our context, the first variation to the higher world global charges associated with the symmetric vector field zeta can be written as the contribution from Scri plus and the contribution from I plus. Here, omega is the symplectic current, and in omega is the normal to the Cauchy surface that we consider. So to study the contribution to the global charges from I plus, we choose the hypersurface to be a tau equals to constant hypersurface. The volume factor root h d cube x that we have just shown rose as tau cube in the tau tends to infinity limit. On tau equals to constant hypersurface, this omega gamma n gamma can be written as is equal to the tau component of omega, and the final expression for omega reads omega tau equal to 2 over tau cube times the first variations of the field sigma and k. So now one can see that if one uses the boundary condition trace of KAB equals to 0, the first variation to the higher world global charges vanish, which implies that the symplectic flux, the contribution to the symplectic flux from I plus also vanishes. So one can now construct future localized charges on a two-dimensional surface which encloses the sources at time like infinity. So we do that. So in this slide, I will talk about the localized charges, and motivated by the work at special infinity, especially the work of Compare and Dehu, we take the super translations of the form box minus 3 omega equals to 0. Then we can define a localized charge q omega, which is given as the integration over a spherical cross section C, which encloses the sources at time like infinity, and q here is the induced metric on the spherical cross section C, and RB is the unit normal to the spherical cross section C, which is embedded in the hyperboloid. So this form of q omega is our proposal. However, we have not done a first principle derivation, and it can be done by relating this charge, this q omega charge, to the charge contribution from the future boundary of the future null infinity, which is Scri plus plus. So since there is no symplectic flux, that is the first variation to the higher world global charges vanishes, This expression is independent of the choice of cross-section C. Similarly, we can define a localized charge associated with Lorentz symmetries by considering a conserved tensor JAB, where the divergence of JAB is equals to 0, and this JAB can be constructed from the second order fields. Okay, so to understand what are the cross sections that we are taking, I draw this diagram, and here one can see that this curly H is the Euclidean ADS3 hyperboloid, and the spherical cross section C is here denoted by this circle C. This is embedded in the hyperboloid, and it encloses the sources at time like infinity. So do I have some time to talk about Schwarzschild solution?
I think in the next 1 minute we should try to wind up.
Okay. Okay. So in this section, I will talk about the Schwarzschild solution at a time like infinity. So we write the Schwarzschild solution near time like infinity in the Bike-Smith form by doing a series of coordinate transformation. The requisite Bike-Smith form at first order in expansion of 1/τ not only satisfies k equal to 0, but it also satisfies the boundary condition KAB equals to 0. Then the field sigma takes the following value, minus GM times rho inverse plus twice rho, and it also satisfies the box equation. Here one can see at rho equals to 0, sigma blows up. So this is a cartoon diagram of the intersection of the time like future time like infinity and the future horizon. So here the curly H is the Euclidean ADS3 hyperboloid, which denotes the future time like infinity, and the cross section is seen here as a circle. But as one goes near tau tends to infinity, the circle now pinches to a point. So we notice that, I mean, why do I draw this diagram? Because we notice that as tau goes to infinity for fixed r, rho goes to 0. Thus, the horizon r equals to twice gm intersects the time like infinity hyperboloid at the origin rho equals to 0. And as I was saying, at rho equals to 0, the field sigma blows up. So for the Schwarzschild solution, the field sigma and H1AB are singular at rho equals to 0. However, the charge integral is finite even on a rho equals to epsilon spherical surface, which is again defined as q omega, which is equal to the integration over the spherical cross section C, which encloses the sources. And for the region r greater than twice gm of the Schwarzschild solution, time like infinity is taken to be the hyperboloid minus the origin. Thus, we see that for a gravitationally bound system, the origin at time like infinity acts as a source for the charge integrals. Okay, so I will summarize. We start by defining asymptotic flatness at time like infinity. We then studied the action of supertranslations at time like infinity on fields at second order in 1/τ expansion. We used our boundary condition to show that the Lee-Wall symplectic form does not receive any contributions from the time like infinity. Finally, we proposed expressions for the supertranslations and Lorentz charges. As a future direction, I can say that one can follow the work of Troisert and Prabhu, and then we, I mean, if one follows that, we expect that our charge expressions can be matched with the appropriate expressions for supertranslations and Lorentz charges at Scri++. Another important question to answer is that can our boundary conditions be one can also study their role or the action on the asymptotic fields at time like infinity. So thank you for listening.
Okay, thank you very much, Debodirna, for the nice presentation. We are slightly running over time. There is a quick question that we can take up. Otherwise, I will go to the next speaker, the last speaker of this session.
Hey, Deepak,
yeah.
can I?
Thank you.
Yes.
Yep.
Yes.
Did you have any massive particle in your theory at all? Or was it just Einstein gravity?
So no massive particle. I mean, so I don't understand. I mean,
no, I mean, if you just had Einstein gravity, then you wouldn't expect any charge at time like infinity, right?
Yeah. So right. I mean, no. So what we have done is we just say that the I mean, for a particular boundary condition, the charge is 0. So I mean, the flux is 0. So then we construct a localized charge that that remains invariant under this. I mean, whatever remains. I mean, whatever surface, whatever spherical cross section you take. Yeah.
Okay, I think let's thank Debodirna again for the talk. You may stop sharing your slide. Parthiv Haldar, is Parthiv here? Is Parthiv Haldar here? Sorry.
Hi.
No, sorry, Akhil Sivakumar, sorry.
Yeah,
Akhil Sivakumar.
Can you hear me?
Yeah. Yes, we can hear you. You may share your screen.
Okay.
And I will stop you at 13 minutes. So in the next 2 minutes.
Okay. So you see my screen?
Yeah.
Okay.
Yes.
So
now our last speaker of this session is Akhil Sivakumar. I think I missed him. So he will be talking about the fluctuating hydrodynamics via holography. Yeah,
okay.
Akhil, please.
Hi, I begin by thanking all the organizers of ISM for giving this opportunity to speak, and in general for organizing such a nice week of seminars. So I'll be talking about fluctuating hydrodynamics via holography, which is a general perspective on the kind of projects we have been doing in over the last 2 years, which is to look at general real-time ADS-CFT calculations in a particular way. I'll be mostly talking about this work here and a bit about this work. And this work is also like an ongoing thing, which is on the same set of concepts. And then this is my extended list of collaborators. So let me start by motivating the problem. So we know the fluid gravity correspondence maps long wavelength deformations of dual black plates to long distance excitations or hydrodynamics of holographic plasmas. The original fluid gravity program analyzes Gaussian normal excitations of black plates. They find there are long-lived Gaussian normal excitations, and then you rewrite the boundary stress tensor in a fluid appropriate way, and the conservation of the boundary stress tensor then gives equation motion for the boundary fluid. To summarize, over large distances, the plasma behaves like a dissipative fluid governed by a Navier-Stokes equation. But we know that a dissipative fluid description is only an approximation to the more complete picture of fluctuating hydrodynamics. So the reason is that the microscopic modes which cause dissipation also affect the hydro description as some stochastic forces. So this should be thought of as a fluctuation dissipation relation. And in addition, there are statistical fluctuations of the hydrodynamic modes themselves, which are long-lived. And then, as you realize that once you start accounting for these long-lived long-lived fluctuations, it kind of makes your hydrodynamic theory sick. And you can check this reference for some discussion of this. So to understand this paradigm a bit, we could consider a simple toy model, which is like probing a fluid with a particle, say considering a pollen moving in air or something. So at low energies, we see only hydrodynamic modes. The presence of microscopic modes like molecules themselves is diagnosed from the Brownian trajectories of the particle. The lesson is that the low energy description is an open FT field theory of the hydrodynamic modes and probes interacting with microscopic modes, say molecules. In other words, the fluid has fast relaxing or Markovian modes. That's my definition of Markovian for the context of this talk. And long-lived or non-Markovian modes. We may integrate out the fast modes while retaining only the slow modes of the fluid to get a Wilsonian open EFT. And you can refer to Loga's talk on Tuesday for like a detailed, more elaborate motivation of this. So having motivated the Wilsonian EFT perspective for fluctuating hydrodynamics, there are two technical questions to answer. First is that given a model, how do we indeed separate out slow modes from fast modes and selectively distill them out? And this talk is mostly about that. I'll motivate a formalism which does this, at least for holographic systems. And then the second question is, how do we incorporate the effect of statistical fluctuations? So from the field theory side, you would say we have to study the field theory as a Schwinger-Keldysh path integral, where you track the evolution of the whole general density matrices, or mixed states rather than pure states. And in holographic models, we know that boundary statistical fluctuations are dual to Hawking-radiated modes from the black brane. So what we do is we use a novel Schwinger-Keldysh version of black brane geometries. So for those who know what a Schwinger-Keldysh path integrals, it's a double path integral and so on, which you kind of mimic by using a glued double black brane solution and so on. I might not be able to go into the details of this construction because of time constraints, but hopefully we will. But this is the short summary of how to deal with the second question. So this is the outline for the talk. So I'll talk about distilling out the fluidic modes. Then I'll give an example of the final goal, like how to understand this paradigm of Wilsonian EFT by considering the example of deriving a nonlinear Langevin equation for a Brownian particle in the holographic plasma, which considering a dual string moving in the bulk and so on. And then if time permits, we will talk about Schwinger-Keldysh black branes, and then we will summarize and then float some future directions. So, like I said, we need a general prescription to separate out Markovian and non-Markovian dynamics. Focusing on a d-dimensional CFT, a working principle seems to be to implement an SO_d-2 harmonic decomposition of the excitations. So this is plausible from the bulk as for generic manifolds of time M2 times SD-1, where the 2 and d-1 denote their dimensions and S is some maximally symmetric space. This separates out Einstein and Maxwell perturbations into gauge invariant sectors. Why Einstein and Maxwell? Because we are interested in the long distance regime, and the players there are all the conserved quantities like energy and charges and so on. We are motivating a setup where like hydrodynamics modes are labeled by the wave vector k and the representation of transverse SO_d-2 rotations to this k. So this is similar to the way we think of particles as labeled by their little group representations and so on. So there are like this is some notation setting up, like these are tensors and vectors and scalars of this such a harmonic decomposition, and there are so many of these guys. So our proposal is that each of these excitations of the hydrodynamic theory dualizes to a bulk scalar, which is, so to speak, a master variable in the bulk, which captures the dynamics of bulk fields, the Einstein-Maxwell fields in the bulk. So more explicitly, the bulk solutions for Einstein-Maxwell fields can be written like this, where you see these phi d minus d, phi 3 minus d, and so on are the master scalars I mentioned, and they capture the bound. They do a harmonic decomposition of the sources, and then of the dual boundary currents and so on. To see this, like if you have a U1 current in the boundary, the spatial current can be decomposed by this SO_d-2 into some vector and scalar, and then you see that since the vectors are transverse, they are trivially conserved. And in some sense, there should be, that kind of indicates there should be short-lived modes because there's nothing non-trivial going on there. And indeed, you find that only JS leads to non-trivial dynamics, and it shows charge diffusion and so on. Similarly, for the stress tensor, you can decompose the tensor, the stress in the SO_d-2 fashion, and then the tensor part here is trivially conserved and doesn't lead to any non-trivial or long-distance dynamics. It's a short-distance mode. And the TV and TS denote transverse momentum diffusion and pressure waves respectively. And the cute fact about at least these four sectors explicitly written here, if you notice, I have like kind of like suppressed the details on the scalar sector of the gravitons, is that all these scalars come from satisfy equation motions which extremize a simple one parameter action like this, which is a dilaton deformed Klein-Gordon action with a simple index m, which we call the Markovian index for obvious reasons. And then these M's can be mapped to each of these sectors I have explicitly written by this identification. And the thing about the scalar sector is that the action is slightly more complicated, but it is almost along the same thing. So the thing you have to notice here is that for these things, these sectors which I advertise as short scale sectors, short-lived sectors, the scalar directly maps to the gauge field in the bulk. But for these long-lived sectors, it is actually the radial momentum of the scalar which maps to the gauge fields in the bulk. So the fact about this general class of scalars, their equation of motion and their solutions and so on, is that when you compare the boundary radial momentum, 𝝅m always have derivative. 𝝅ms always have derivative expansion in terms of the boundary value of the field itself. So based on this like a difference on what is the bulk gauge field, whether it is 𝝅m or 𝝅m, this is interpreted as a local expansion for the sourced Markovian fields and the equation of motion for the non-Markovian fields. So the boundary condition for the Wilsonian EFT is to fix boundary sources for m+1 greater than 0, which are the Markovian modes, which directly map to the gauge fields, and 1-point functions for the m+1 less than 0 modes, which were the non-Markovian fields. This is like explained more by Loga in his talk. So this is a table summarizing these boundary conditions. For the Markovian sector, the usual so this first column is a Markovian sector, second column is a non-Markovian sector. The usual GKPW's boundary conditions, which tells you how to calculate correlation generative functionals, will tell you in the Markovian sector you have to fix 𝝅m, and in the non-Markovian sector you have to fix 𝝅m. But in the Wilsonian boundary conditions motivated here, says you go to this field basis of effective dual scalars, and then you fix the 𝝅m, like you put Dirichlet boundary conditions for both all scalars. So like I've talked about decomposing these scalars, writing FT theories, like suggested Stringer-Kalish, Path-Nichols, and so on. But how do you indeed make sense out of this, right? A simple way to make sense of a Wilsonian EFT is by mapping it to a stochastic differential equation. There's a general procedure to do it, as done by these guys. So as a simple example, consider again the particle probing the plasma, the Brownian particle. The bulk is dual. In the bulk, the particle dualizes to a string which starts from the boundary from the particle, but then goes all the way to the black brane and dips into the horizon and so on. A nonlinear Langevin equation for the Brownian particle can be derived from the bulk dynamics of the Brownian string, which looks like this. So you notice that in addition to the usual dissipation and the stochastic force, you have a usual drag and stochastic force. There's a part of the drag which is stochastic itself, right? And it comes with a coefficient zeta gamma, and the stochasticity is captured by the same noise variable. And in addition to the noise, in addition to a simple Gaussian nature of the noise variable, so it's no longer Gaussian. It has non-Gaussianities captured by some parameters like this. There's some mainly the zeta n, which is a non-Gaussianity parameter, and then as in the familiar case, there's a fluctuation, the usual fluctuation dissipation relation, which relates f², which is the variance of the noisy force with the drag. Now there are additional nonlinear fluctuation dissipation relation, which relates the non-Gaussianity in the probability distribution to the nonlinearity in the dissipation, right? So how do you go about doing this in the bulk? So how do you capture these nonlinear corrections? As general, you have to more than the linearized equation of motion for the string, you have to add in interactions, like nonlinear corrections in the bulk. And then this noisy part really comes from doing a careful analysis of the Hawking radiated modes of the string. And it's crucial to include them correctly. And it's crucial to include them correctly at the horizon and so on. And that's the crux of all this calculations, that you have to carefully account for Hawking radiation to see the effects of fluctuations in a consistent way. And the signature of the consistency is these fluctuation dissipation relations, which have been indeed derived independently from the field theory side, like in this work. and like by assuming some weakly coupled path and all. But the point here is that you naively impose you go ahead and like accommodate Hawking radiation effects in using our techniques, and the bulk calculation directly gives you these and which are consistent. How much time do I have left?
You have 2 more minutes left.
Okay, so maybe I'll like quickly go through Schwinger-Keldysh path integrals. So open systems are described by reduced density matrices. The natural generating functional, once you consider density matrices, so general mixed states are like correlators, general correlators like this, where you can like general correlators where you can like act with operators on either side of the density matrix, and the path integral realization of such a calculation would need you to really act with operators separately on the left and right side of the density matrix. And then the appropriate path integral is defined on a closed time contour, okay, where the upper and lower legs on this time contour really denote the left and ket and the bra evolving forward, and you kind of think of the bra as evolving backward, and then they are identified at some future time point indicating this tracing. And this is like a cartoon for creating some initial thermal density matrix by evolving with some beta time and so on, which is more familiar. And so there's a bulk realization of this. So the point is now that how do we like go about doing such a calculation in the bulk, and why is any of these calculations new or only possible at this point, right? So the point is that like you have to realize these bulk calculation, especially CFT path integrals of this kind, Schwinger-Keldysh CFT path integrals from the bulk, and which involves understanding the gravitational saddle which really captures this path integral. And such a workable prescription, I should say. Like there have been attempts at deriving such an object before, and this is a workable prescription for doing these calculations, where they think of this black hole as a complexification of a usual short shell black hole, where you consider the black hole at a single in the ingoing Finkelstein time, which is crucial. And then you consider a single time slice of the black brain in ingoing Finkelstein time, and then you say like the fixed time radial coordinate has this analyticity. So whatever excitations you trigger on this, black brain should have this analyticity condition. That is that at a fixed time, if you consider a radial contour, the solution should be analytic on a contour like this. So you'll notice that like there are 2 asymptotics now, which is good because we wanted a path integral where there are 2 CFTs, one for the ket evolution and one for the bra evolution. And the idea is that you end up getting some black hole saddle like this, this is some exterior region, 2 copies of it glued along some horizon, say this shaded region. And then in the far past, you probably have like this is a cartoon picture, like this not. But still, like you have a past thermal circle in the boundary and a Euclidean black hole in the bulk and so on. So, but I should maybe add that like this is a prescription, and it seems to give you consistent answers even when you really do calculations with Witten diagrams and so on, like say contact interaction Witten diagrams and so on. So let me summarize. I motivated a formalism to distill out fluid modes of different hydrodynamic natures and introduced alternate boundary conditions appropriate for the Wilsonian FT field theory. So these are the future directions. Like one would like to understand these calculations as you consider bulk exchanges in Witten diagrams and even bulk loops and so on, and which is crucial to understand the phenomenon of long-time tails in hydrodynamics, which is the fact that correlation functions don't really decay as you expect. This is part of the sickness I mentioned in the motivation. So then you might want to go further and derive the saddle, because as I said, it's a prescription. You might want to understand why is the structure of black hole geometries true, as in like you think of them as analytically continued in radial coordinate or something, and then it seems to give you the right Schwinger-Keldysh coordinates. And you might want to even go further and describe such a saddle away from equilibrium, like because at this moment you're thinking of a black brane, the ordinary short shell black brane, but then perturbatively excited. But you might want to derive a Schwinger-Keldysh saddle for like configurations really away from equilibrium corresponding to away from equilibrium boundary plasmas and so on. That's it. I thank you all for your attention.
Okay, thank you very much, Akhil Kumar, for your nice presentation. If there is some short questions we can pick up, we are already late because the next session starts at 2.
Okay, I had a. Can I ask? I had a small question.
Sure. Yeah.
Yeah. So actually, yeah. So this the scalar. I mean this decomposition you introduced into Markovian, non-Markovian. Maybe I missed it. I mean, is it related to how these modes couple to gravity in the bulk somehow? That I mean, what is this classification?
The classification simply is that simply from the hydrodynamics, right? It's just the fact that if you can decompose a current in this way, like here, and then if you can calculate the correlators of the current, the Markovian guys have short scale correlations, and the non-Markovian guys have long scale correlations. And then when like in usual case when you derive the EFT, you don't want to integrate out the stuff which has long scale correlations, only the stuff with short scale.
So my question was about the action you have written down actually. Yeah. So there's this coupling through this kappa. So is a statement that somehow the M, depending on how the coupling becomes stronger, it's weakly coupled in the bulk, then it is one class of modes. It's the hydrodynamic mode.
Yeah.
So that's the classification, right? So is that
so it okay. So just looking at the effective scalar action for these bulk scalar modes, it seems like you're modifying a Klein-Gordon scalar by amplifying either its bulk dynamics towards the boundary or either towards the horizon.
Exactly. Is that the distinction between the two?
So from the perspective of just the equation of motion, that seems to be the distinction. Yes.
Okay. Thank you.
And but it's non-trivial that at least these 4 sectors you can have a uniform like a simple one parameter classification of these modes. Yeah.
So this dilaton kappa basically tells you that.
Yes, right. Yeah.
Okay. Thank you.
Yeah, thanks for the question.
Okay. Yeah, if there are no other questions, let us thank Akhil for a nice presentation.
Yeah, thank you.
Over to the host.
All right. Thanks, Kamal. Thanks to all the speakers. So, like always in this conference, let us reconvene at 2:15, 2:15, 2:15. Thanks, everybody. And again, we'll be using a different post-lunch Zoom link to do so. See you then. Bye-bye. Thanks. So team, we can end the recordings and close the meeting.